Hi guys, I'm just gonna wait for a bit more. Appreciate you guys coming right on time. I'm gonna wait for like 5 minutes and then we'll get started with the chemistry course. Grab your pen, grab your paper, grab some food. I'm on live on TikTok now as well. Perfect. Cool. Hello guys, hello guys. I'm gonna give me like a bit more for the guys to just join up and then we'll get started. If you want to get your calculators ready, because we're going to be doing quite a bit of maths. As you know, chemistry is very maths heavy anyways. So yeah. Hi guys on TikTok. Just join up on YouTube. Go into my the link in my bio and just join from there, and then we'll get started very soon. Hello everyone. Hello, hello, hello. Cool. What we're going to start off with at the beginning, we're going to be probably looking at, not probably, we are going to be looking at the time of flight stuff. And then we will develop throughout, essentially just more or less all of inorganic. Like 80% of physical, because, you know, we have to look at time as well. Like the big chunky markers, so we've got acids and bases, we've got time of flight, we have transition metals, we're going to be looking at the group 7 equations. I'll tell you all about the catalysis equations. I'll give you every single equation. When I was learning myself, essentially I took time to, you know, write out every single equation. And I knew that I was doing this from year 12 actually. How long will this take? This is going to be, it's a 4-hour lesson. So we will finish at 7 p.m. If I feel that we are running out of time in some bits, I will kind of skip over because I've got acids and bases right towards the end of this here. So if I feel that if you're taking too long or if we're running a bit out of time, then I'll kind of skip ahead. But inorganic is mainly memorization. I will tell you every single equation. You guys can like cram that. Yeah, it will be posted on YouTube. I'll try my best for electrodes. Honestly, I'm gonna be honest. I haven't got anything planned for electrodes. There are 89 slides, so there's quite a bit. And I have no idea if it will be, if I can fully fit this within 4 hours. There's like a lot of, it's just all of physical, more or less all of physical, more or less all of inorganic. The big chunky markers. If there's anything specific right at the end, if we have time, I don't mind going over. But I don't know if we'll be able to go over electrodes. Because I don't have anything planned for that. But I will try my best. Because some topics we might actually end up going through quicker if it's making sense to everyone. Then we can just fit in. Thank you very much, Ethan. I appreciate that, bro. Honestly, like, that's your hard work, bro. That's your hard work. How did maths go? And how did bio go? Because I know I haven't been live since. I've been talking to my students about it, obviously. I heard bio was absolutely disgusting. I need to see the paper. I haven't managed to see the paper at all, like anywhere. So I really need to see the bio paper. Damn. It's just literally just maths. Eesh. For the guys on TikTok, yeah, like I'm kind of looking over the chat there. I have the YouTube one right in front of me. So if you guys come over to YouTube as well, that'll be better. Base of the online mathematics. Is that come on, Ethan. You can. We're gonna be looking at. Come onto my bio. It's the same username, StudySphere Tutors. But if you go to my bio, it's a link tree. Click the link tree. You'll see chemistry revision. Click that, and then it takes you directly there. Just click the link tree. Okay. We'll give it 2 more minutes, and then we'll get started, guys. Yeah, just join from YouTube. Come on, yes, so smart. What topics am I covering? I'm doing a lot of physical. We're doing actually I made a list. Let me look through what I said. I said electrodes in the video, but I don't think I'll be able to do electrodes just because of time. I will tell you. I've got it in my PowerPoint as well, actually. We got acids and bases. We got group 2, group 7, transition metals and its equations. Group 2 and group 7, their equation. Both Haber cycles. Period 3, we'll kind of look over. It's not that bad of a topic, but all of the equations for that. Time of flight, mass spectrometry. We'll more focus on the electron impact and electron spray stuff, but we'll go over that anyways. That's a very small topic. Ion testing, potentially. We'll go over. That'll kind of be on group 2 and group 7. We'll look at the testing for that. Hess Law. That's going to be after that's going to be before the Born-Haber cycles. Redox titration, reverse titrations. That's the main focus for today. Yeah, that's the main focus for today. AS content. You can think of this as AS content. So group 7 would be considered AS. So if you're year 12, it's definitely helpful for you. Hess Law is year 12. Time of flight is year 12. It's mainly AQA. It's AQA focused. Yes, it will be being uploaded. Is paper 1 content? Yeah, today, yeah. This one. Do you have set times you do this? Honestly, no, I don't. I kind of make a video beforehand. Like, I posted a video yesterday. I was supposed to post it beforehand, but if you join my Discord as well, yes, Bean, how are you, man? If you join my Discord as well, I kind of let people know there beforehand. Like, they're the guys that kind of know. Like, I'm very active in my Discord. So if you guys join, it's pretty nice Discord. It's really nice community. So if you click on the link tree, or if you're in the YouTube live now, you know what? Let's get started, guys. Let's get started. All right. For the guys that don't know me, let me make this full screen. My name's Anas. I got 3 A stars, 1 A. I'm a gap year student. I'm a previous dental applicant, but plans changed, and I'm now going to economics for LSE. I've had loads of years of teaching. 3 years, not that many to be fair, but I think it's a nice number. I started teaching when I was in year 10, late year 10 actually. I've got plenty of students for A-level maths and chemistry. I've got more year 12 students than year 13 to be fair. But the guys who are year 13, they're doing amazing. But yeah, let's just get started. Let's get right into it. If you have any questions, definitely let me know. Put it into the chat, and I will try my best to answer. And I can. By the way, let me go back. The A was in bio. That was 1 mark away from A star. I got it remarked. From 2 marks, 1 mark. You might be asking why am I not a dental student? Not because of my grades, but I just didn't get through my interviews. But yeah, man. I can't lie, Anya. It's just that's long, you know. It's gonna be 4 hours, so literally after 7 p.m. it will get uploaded straight away, more or less. But yeah, good luck for the psychology, guys. 1 second, let me get the TikTok up on this screen. It's 4 hours, so we'll finish at 7 p.m. If you come on to YouTube, so the guys that are on TikTok, if you go into my bio, there's a link tree. Click the link tree, and then there's a chemistry just live session. Click that, it'll get uploaded right to YouTube straight away. So you guys can check that out. I will try my best to cover as much as possible abs. I don't think I'll be covering electrodes in this, I'm going to be honest. But right at the end, there is time, potentially. Okay, alright, let's get started, guys. We're going to be looking at time of flight at the beginning, and oh, this is actually really small. Oops, let me make this a bit more bigger. So, time of flight, I think, is a really nice topic. I think I'm going to say it's 3 marks if you know what you're doing. So, time of flight is, I'll kind of guide you through this, but I want you to have a look at the question, attempt it yourself, and essentially what your whole idea of using with this question is 2 things. For this second part here, we're going to be using our equation of half mv squared. And this first part here, the key thing is really thinking about your Avogadro's constant. So they've given you this, to be honest, it's 6.02, but actually it should really be 6.022, but we'll use 6.02 for the sake of the question. Oops, why has that happened? Okay, we'll use 6.02 for the sake of the question. Make sure you have your calculator ready, because we're going to be doing a lot of stuff. Alright, Anya, take care. But if you are OCR and Excel, you do not need to worry about time of flight questions yet. Or at all, actually, I take that back. So this is only for AQA, so if you want to come back later on, we're going to be looking at some, what we're doing after this, I can't remember off the top of my head. Group 2, I think we're doing after this. But yeah, OCR students don't need Group 2 either, so you guys, no you don't, you do need Group 2, you don't need Group 7. Okay, but anyways, let's look at this first part. We've got calculate the mass in kilograms of one atom of a 72 germanium ion. Where it says atom, but essentially all of your mass spectrometry, and you guys can listen to me while I'm blabbing on in the background, and do this question as well. If you got the answer, just put it into the chat. But essentially, it's too blurry, you can't really see the question. If you guys on TikTok and you can't see the question, comment to YouTube. Okay, comment to YouTube. Yeah, I'm going through transition metals. No, Himera, this is not necessarily you don't need this for OCR chem. No, time of flight is not an OCR chem. You don't need this. Okay. OCR, thing is with Group 7, Elizabeth, is very, very brief compared to AQA. So the equations that we're going to be doing today for AQA, OCR, you do not need them. You just need the ion testing, and that's about it for Group 7, Elizabeth. Okay, I'll explain when I get to Group 7. Come to my link tree, and you'll be able to click it. Or if you can't find my link tree on my bio, sometimes it's glitched, just type in Study Sphere Tutors on YouTube, and you should be able to find it. Okay. But essentially with time of flight, you have 3 stages. One of your stages is to ionize your atom or your molecule. The next stage is to accelerate the molecule. So it's an accelerator. And within this accelerator, what you have essentially is a negative plate. And sometimes in AQA, they ask you about kind of like 1 markers and stuff about this, okay? This negative plate attracts your positive ion. And what happens is, oops, I think my pen's going to randomly, oh no. That's not good. Okay, there we go. I think my pen is going to bug sometimes. You're going to have to bear with. Sorry about that. I'll try to keep my pen away from the screen. Anyways, what happens is your positive ion gets attracted to the negative plate, and then it just gets slingshotted almost through the spectrometer. It's called the mass spectrometer. And what happens is, eventually, it hits a detector. Okay, now this detector will essentially give electrons back to the ion, and it creates a current. Okay, bigger the current means more abundance, there's more of the ion. Okay, these are essentially, this is kind of like your 1 markers and 2 markers that may come up about your mass spectrometry, which may be useful. And we'll look at the questions in a second. Study Sphere Tutors, this is chemistry, Ryan. Okay. What else do we need to know about this? The higher, the more the mass of ion, the longer it takes. Okay, that's something to take note of. In terms of your calculations, if you feel like, okay, if you have a 72 ion and maybe a 76 ion, the 76 ion is going to have a bigger time. For example, this question here, in this case, we're not really using another ion, but a 76 ion will take longer to hit the detector. Okay, for the first question, we're trying to work out the mass in kilograms of 1 atom. Well, we know that in 1 mole we have 72 grams of this. Okay, in 1 mole you'll always have that amount of grams of the MR. So if it's oxygen has a mass of 16. Oxygen has a mass of 16. So in 1 mole you have 16 grams of oxygen. Am I going to do this for biology paper 2? I am not. I hate teaching bio, man. Miss Estrich is your guy for that. I'm honestly, if I was more confident on my bio, I would. But I'm not going to be, unfortunately. Sorry, I'm sorry. I know bio is Friday. I know bio 1 was horrendous, but you guys got this. Yes, Zach. This is only for AQA. This topic anyways is for AQA, so if you guys are doing OCR or Edexcel, do not panic. Yes, Zach. Anyways, we'll continue on. We need to figure out how many, well, we're thinking about how many atoms. Well, we know there are 6.022, I'll stick with 6.02 for the sake of the question, atoms in 72 grams. So that means that one atom will be this number divided by Avogadro's number. So you're going to do 72 divided by, I'm going to put L. The reason why I'm putting L is this kind of like the term for it. And I'm going to bring my calculator up real quick. And in the calculator, you're going to type in 72 divided by 6.02. I'm going to put that in brackets actually. 6.02 times 10 to the 23. And equals, now this is in kilograms, 1.196. 1.196 times 10 to the 22 kilograms. Is it in grams? Sorry. It's not kilograms. Sorry, I take that back. Sorry, that's in grams. So we didn't divide yet. That's in grams. To convert to kilograms, we need to divide this by 1,000. So you're gonna get 1.196 to the times 10 to the minus 20 divided by 1,000 times 10 to the minus 25. Okay, and sorry, there should be a minus there as well. So your final answer should be 1.196 times 10 to the minus 25 because you've converted from grams to kilograms. Okay, cool. Now this is AQA Chem. This is a very small topic, but I think it's a very nice topic. Okay, I'm gonna rub out some of this stuff here, just so I have a bit more space, if it lets me rub it out. I don't know why it's laggy. Maybe I've got too much writing on the screen, that's why. Apologies for the lagginess. Okay, appropriate, it's fine. You won't lose marks. It's better to be more accurate. Okay, having this number is better. Okay, and to be honest, in your real exam, I don't know why 6.02. I think I got this from a or this maybe an older spec question. In your real exam, you will have 6.022. Just be aware of that. Okay, but honestly, you don't really lose marks. Maybe in bio you will, in chemistry you won't. Okay, unless it specifically says round to 3 significant figures. If it's appropriate, you should be fine. If it says 3 and you're giving more, then you're going to lose a mark. Okay, in a time of flight mass spectrometer. Okay, so we have kinetic energy question. I always just start by writing the equation down straight away. Okay, so we've been given velocity is equal to time over distance. A 72 germanium ion is accelerated to the kinetic energy. So we've been given our kinetic energy as it travels down the flight tube that is 3 meters long. Okay, so we have 3 meters. Calculate the time taken for the 72 germanium ion to reach the detector. Okay, so we are going to use 2.4, this previous part. We're probably going to be using our mass here. Okay, so I'm going to expand this out, but just by substituting my velocity formula into here. So I have kinetic energy is equal to a half. This is only AQA chocolate chip. This part's only AQA. A half times by mass times by distance squared over time squared. If this had 3 sig figures, it would be 1.20 m. 1.20, not 1.2, 1.20. The 1.20 is needed because it's 3 sig figures. Okay. Next, what we're going to do is just substitute all the numbers in. So what I'm going to do is 3.98 times 10 to the minus 16 is equal to a half times my mass. Now my mass, I already worked out mass right at the beginning here. So that's going to be 1.196 times 10 to the minus 25. Okay, because I'm trying to work out the mass of the 72. Sometimes it will give you a different ion and you will have to work out the mass of that separately again. So take note of that. Okay, distance we already have as 3 meters. Okay, divided by, or this should be 3 squared, divided by time squared. Now what we're going to do is we're going to go ahead and rearrange this equation. So we have, what we can do is actually get rid of this half. How can we get rid of this half here? Well, we can times both sides of the equation by 2. So I'm going to go into the calculator and I'm going to do 3.98 times 10 to the minus 16. Okay, times by 2. What happens is that a half goes. I'm going to slightly speed this up as well, by the way, for the rearranging. So we're going to divide by this number here. That's going to be our original mass that we worked out earlier. And we'll find out that we end up, oh, that's a weird number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6.68. 6.66, sorry. 6.66 times 10 to the 9 is equal to 3 squared over t squared. We're going to rearrange this. Oh, I can't lie, I did this on PowerPoint a very long time ago, and I can't lie, I think I made that mistake again. I maybe should have just done it on OneNote. I might move it to OneNote in a bit, because it's just going to keep on bugging like that, and I don't like it. 1 sec. One second, let me bring the calculator back up. Yeah, I can't have PowerPoint, it's annoying. Anyways, we're going to rearrange 3 squared, divide that by that answer, and we're going to square root. And our final answer, what we should end up with when we rearrange for t, we should end up with 3.68 times 10 to the minus 5 as your final answer. Okay, if you got that answer, amazing. T is equal to 3.68 times 10 to the minus 5. Okay, these are good marks. These are good marks. Do I have links to the slides or questions used? What I can do is I can upload the PowerPoint on Google Drive, and then if you want to access that, if you're on an iPad or anything, if you want to take a screenshot as well, that also works. Okay. This question here, we got some abundance. I know we're gonna start off easy. I know some of these questions aren't that bad. We're gonna up the difficulty later on. If you guys are finding time of flight very, very nice, then we're gonna move on to the harder topics. Okay, have a go at this question. Let me know what numbers you get. If you're happy with the numbers, we will just move on. What I will do though is let me upload this drive link, and then I'm gonna just attach it on my link tree. 1 second. But if you got the answer, just put it in chat, and we'll double check for part 1 and part 2. And if you're cool with that, then amazing. One sec. My drive. Where is it? Share. I can put it in chat. Should I put it in chat? Yeah, I'll put it in the YouTube chat. 1 second. Can't we do separately, like work out the velocity first and then put velocity in the kinetic equation? What you can do is you can rearrange. There's not one way of doing it. As long as you're rearranging and essentially working out time, you should end up with the same answer. That's the thing with maths; it's very consistent. That's the link for the PowerPoint. Whoever was asking for that for the link, I'll just put it into YouTube chat. Okay. Give the formula of the ion that will reach the detector first. Well, the detector. The one that will reach the detector first will be the lightest ion, so it's going to be it hasn't really said, has it? But germanium, I'm assuming it is germanium 70 plus, because make sure you put ion. Okay. Right, part 2, use the data in table 2 to calculate the relative atomic mass of the sample of germanium. What I'm actually doing, I might just move to OneNote in a second, because yeah. If you guys have got the answer 72.4, can we confirm with that? We're getting 3 72.4s. How can we work this out? We're just going to multiply by each of the percentages, and then we're going to divide by 100. Cool, amazing. 72.4. Alright. Very, very good. Next, let's just move on. Have a go at this. Let me know what you get for this. I'm going to set up the OneNote real quick. And that's what I normally use to teach. I thought maybe PowerPoint might be just a bit nicer, but clearly not. Sorry about that, guys. Okay, yeah, this is good. This is good. Yes, we are 100% timer. We are 100% going to be going over the transition metal colors. I'm going to move this to the other side. For the guys that have got the PowerPoint, just keep on looking at that for the questions. I'm just going to be copying over the questions across. I think it's just nicer to have it a bit more smoother. Okay, I think that's good. All right, cool. 53 chromium ion, we've got a kinetic energy equation. We're going to just substitute it in and then just work out the time. This is going to be mainly to do with your maths. Yeah, we're going to be going over period 3, hopefully, yes. This is AQA, Fanta. It's AQA. But for you guys that are at Excel and OCR, you're more than welcome to stay. The guys later on, we're going to be looking at more of the other paper one, inorganic and physical stuff, so do not worry. Okay. Alright, while you guys are doing that, I'm just going to start off with the kinetic energy equation. And what I just like to do as well is just convert this velocity. Sometimes they'll give it to you, sometimes they don't. Just substitute speed is equal to distance over time. Just sub it in. Okay, and I'm going to clean this up to make this a bit more look nicer. Like so. Okay, if you're confused of where I got this kind of numbers from, or this equation from, please ask. But essentially, I've just substituted velocity into here, and I've just cleaned it up to make it look like a nicer fraction. Okay, now we have we're trying to essentially work out time, and I'm just going to substitute all the numbers in. I've got my kinetic energy, which is 1.102 times 10 to the minus 3. Check that again, Kaido. It's not going to be 7.9. There's going to be times 10 to the something after that. It is probably 7.9, but just check. Is there times 10 to the minus 23, 13? What is it? Okay, because that's way too big. It's equal to, and I'm just substituting the numbers into this formula here. Mass is going to be, well, we have to actually work out mass as well, so we haven't got the equation for mass. If you guys are confused how to work out the mass of one ion, it's going to be the exact same thing as before. 53 is 1 mole. Okay, I made a quick formula of what you can do to work out the mass really quick in terms of kilograms. What you can do is just do 53 divided by 1000 times by the Avogadro's number, which is just L. If you put that into the calculator, that gets you the following: 53 times by, 53 divided by 1000 L. I've got L stored in my calculator. That should give you 8.80. 8.80 times 10 to the minus 26 as 1 gram, 1 atom in kilograms. And then that's going to be your mass. If you're confused on how to work out the mass, please do let me know as well. It looks like we're getting 7.9 times 10 to the minus 7, which is good. If there's an agreement on that, then I might speed it up a bit more. 2t squared. We're going to go ahead and rearrange this for time. And the way we're going to do that is times by 2 and divide by all of this. So I'm going to pull out my calculator again. 1.102 times to the minus 26 times by 2 divided by 8.80 times 10 to the minus 26, also divided by 1.25 squared. And I find that this number here, 0.16, is equal to 1 over t squared. So time should equal to 1 over answer, 1 divided by answer, and square root that. That is definitely not right. I've done something wrong here. 1 second. Times by 2. That's not supposed to be minus 3. That's supposed to be minus 13. Oh, that's why. 1 second here. Where's it gone? Where is it? 1.102 times... Oh, that's supposed to be minus 13. There we go. Yeah, 7.9. Amazing. 7.9 times 10 to the minus 7. That should be your final answer. Okay, perfect. It is a nice topic. You got 8.8 times 10 to the minus 23 instead of minus 26. Yeah, you got to divide by 1000. You want it in kilograms. Okay, because your mass here is in kilograms. So just be careful of that. Okay, and the rest you should be fine with. Okay, nice. Next question. Now, this part here is basically what we kind of went over while you guys were doing the other questions. Explain how the abundance of each isotope is determined in a time of flight mass spectrometer. Well, perfect. It gets what you have is, since it's an ion, you need to say this specifically. The ion gains an electron from the detector, and that is that forms a current. Okay. Yes. Then the abundance, the more the current, the more the abundance. Yeah, we're going to be looking at redox titrations and reverse titrations as well. Okay, perfect. Nice. State why the inside of a time of flight mass spectrometer is operated under vacuum. If it's operated under vacuum, there are no particles that can collide. So if there's air within it, there's going to be air particles that can interact with the ions, and that can cause the ions to essentially bounce off different things. So no particles interact with the pathway of the ion's movement. Okay, actually, while we're here, let me just check the next questions. Actually, no, we'll go over that through the next question. This part, I was going to talk about electron spray and electron impact. I can talk about it with this. Yes, 100%. You can put that as well. That's completely fine. So both are acceptable. Air particles will get ionized. It depends where the air particles are specifically, but in that case, that is still correct. So they'll be affected by the detector, interacted with the detector, and then your abundance will be kind of distorted. Okay, so with this, we've got electron impact and electron spray. You need to know both of your equations. Yes, tell how I use a graphical tablet. I've got a pen. This one's AQA right now, but we're going to be doing like for the guys doing OCR and Excel, you guys can definitely stay or come back later on. At the moment, it's on time of flight, so this is AQA at the moment. Okay. So electron spray and electron impact. So electron impact, what we have is essentially these are more used for your smaller particles, or smaller molecules, I should say, / particles. And essentially what you have is a gaseous molecule here, and you throw an electron at that, and it causes an electron to get knocked off. Okay, both are acceptable. You can write it like this, or you can write it like this, and this is actually the same equation as your ionization energy. Both are acceptable. I'll be live for 4 hours. We'll be finishing at 7 o'clock. But both of these are acceptable. Okay, this is for electron impact. For electron, yeah, perfect. So in this case, it is, what do we have a specific? Yeah, we have titanium, so you want to be careful with that. They haven't really made it clear. But in this case, this would be titanium for electron impact. For electron spray, the difference between electron spray is, I'll give you guys the equation first, and I'll talk about what happens in the background, is you have a, this is more used for your molecules, but what happens is you dissolve your molecule into a solvent, and then you spray it out. I'll write this down: solvent, dissolve, in solvent, and you spray it out through a very thin needle. You can say hypodermic needle, through a thin needle that is highly charged. Okay, and that causes this to react with a proton, and essentially that becomes ionized. Okay, that is your equation for electron spray, and you need to know this. Oh yes, you're right, Kaido, you're 100% right. Yeah, that should be a plus. Which equation of the two electron impacts? Any is fine. They're both correct. Okay, just write one. Solvent, you can say is volatile. You don't need to say it technically is, because that's what the organic thing is. That's what allows it to become a gas, because it's so volatile. Essentially, you're right. That's the whole reason it becomes a gas. But it's just a solvent. You can just dissolve in solvent. But if you want to say volatile solvent, that also works. But the key thing is you dissolve it in a solvent, spray it out through a thin needle which is highly charged. Okay, this is the key bit, and that gives it a proton. That gives your molecule slash particle a proton. This is used more for molecules, and it becomes, well, it gains a proton essentially. It becomes an ionized molecule. Okay, what examples of solvents you don't necessarily need to know, but generally they'll be like hexane, potentially ethanol, that kind of stuff. Okay, but that's where as well when you look at your mass spectrometry the key thing is gains the H plus. That's the key thing. Okay, it doesn't matter what the actual solvent is. For your electron impact, if you use bigger molecules, what can also happen sometimes is that it can cause fragmentation. So whenever you see kind of your mass spectrometry, which looks in different lines, and you'll be like, okay, what do the different lines represent? Why do you have maybe a 20 chlorine when you know chlorine has an MR of 35? It's because it's just kind of broken it up, because it's just, actually that's kind of wrong in terms of chlorine, but it's more to do with your molecules. Maybe let's say you have ethanol. Why is it that you have a smaller MR of your ethanol? It's because it's fragmentation. It's because it's kind of split apart. Electrodes may come up in paper 1, potentially. If they don't come up in paper 1, they'll come up on paper 3. They're a topic that will generally come up. What if you say that the tip of the needle is at high voltage? That should be fine. Won't the proton change the element used? I can see why you're saying that, but the whole idea of mass spectrometry of SMART is to see the MR. It doesn't matter what the actual element is. Okay, you're trying to see, is this the thing? But since you know it's electron spray, if your MR is, for example, let's say in your ion, in your detector, you get MR is 167. Okay, then you know that your original MR must have been MR is 166 because you've just added a proton onto it. Does that make sense? Yeah. So you can subtract one afterwards. Also, something to note. This part I'm actually about to mention. This is actually very relevant to OCR. This part I'm about to mention. So, this part, essentially, what you can have is different MRs. So, you can have different MRs of. I'm going to draw this molecule here. C2H4Cl2. Okay, you can have an MR of. I'm actually going to work this out on my calculator before I tell you guys. Give me a second. 12 plus 4 plus. Okay, you can have an MR of 98. You can have an MR of 100, and you can have an MR of 96. Let me just double check this. I might be wrong. No, 98. 100 and 102. Okay, how does that work? Why is it that this molecule here can have 3 different peaks in a mass spectrometry? This is to do with your isotopes. The whole point, yes, absolutely correct, Imad. The whole point of mass spectrometry is that you can have different isotopes, and sometimes you can have different peaks. And a lot of the times you'll have different, essentially 2 markers, and they're like, why is this a 2 marker when it's like, oh, I don't know what I'm doing. It's not as bad as it seems. And I've seen a question in OCR, this question I've seen in OCR, it says draw the isotopes. Okay, in this case, fair, you can draw the isotopes, but how do you get isotopes with an MR of 102, 198? Essentially, you have different isotopes of chlorine, where chlorine can be 35 or chlorine can be 37. And if I draw this molecule here, I can draw this molecule like so. C and C, H. Let's do H's on top, and a Cl on the side. But whenever you're drawing isotopes of mass spectrometry, or even talking about anything to do with mass spectrometry, always, I haven't got it down here, but always mention the mass number. Okay, always mention the mass number when you're talking in terms of context of mass spectrometry. Just put the number there. So this MR here, if you add the numbers, MRs all together, this will give you 98. But what you can have, sometimes you could have a chlorine 37 as well, and suddenly the MR of this is 100. You could also have 37, which would cause it to have an MR of 102. Okay, that's essentially to do with this mass spectrometry, and you see this a lot more in OCR in my opinion than AQA. This part here, anyways, with this mass spectrometry, especially when you're looking at NMR and IR spectroscopy, that kind of stuff. But that comes. No, you'll be fine with that. I think it's a nice, easy topic. Give 2 reasons why the sample must be ionized. Maybe Kaido, maybe. Give 2 reasons why the sample must be ionized. 1, we already talked about this earlier. This part is AQA, this part is not necessarily OCR. Maya, yes, it is. Good luck for psychology. Smash that, I know, that's your last paper. Where was I? Yeah, so your ion is attracted to the negative plated, that's a positive ion, a negative plated accelerator. Okay, so your accelerator has a negative plate which essentially attracts it and causes the ion to get sent across. Okay, and reason 2, so positive ion can gain electrons on detector to form a current. Okay, these are just things that we've already discussed. Form a current. Cool. Yeah, 100%. Yeah, 100%. I will tell you if it's OCR really or not. 100%. Because this is, I've tried to make it for everyone. I know it's more AQA focused because I do teach OCR though. A lot of OCR you've got less in physical, I'd say, but you've got more in organic in terms of, and even in yeah. Is there another answer that ion can interact and be accelerated by the electric field? The key bit is the positive and the negative part. If you mention that the positive ion is attracted by accelerated by the negatively charged electric field, I'd say yes. Because the key bit is that the ion is positively ionized. That's the key bit. Okay. Next bit. So you can gain a proton. No. Can't I know, man. I'm gonna skip past that. I'm gonna skip past this. Let's do some redox titrations. Or some titrations in general. We're gonna start off with some normal titration stuff. Have a go. Read this question, and then I'll go through this. Okay. On the PowerPoint, some of the questions have mark schemes, some of them don't. So just kind of look through them. If you guys are looking at the PowerPoint while you're watching the video, that's completely fine. What did I get in my A levels? I got 3 A stars, 1A in my bio. I was 2 marks away from A star. Got remarks. Didn't give me an A star. I was 1 mark away then. But yeah. Have a go, and then we'll start on this. What does it mean when the current is proportional to abundance? Yeah, so essentially it just means that the more the current is, the more the abundance is. So if you have, basically it just means that. I'm just trying to think of an example off the top of my head in terms of proportionality. Like let's say you give a guy £1 and he gives you £2 back, and if you give the guy £2, he's going to give you £4 back. So it stays consistent in terms of proportionality. That was like the best example I could come up with at the top of my head. Alright, I'm going to start off with this. I like to rewrite the equation for this. I know you guys haven't finished yet. Sometimes you might not get equations. Sometimes you might have to rewrite the equations yourself. Yeah. Which paper is this from? Kinda, no idea, bro. No idea, Aisha. A lot of the stuff, some of the stuff I got from past papers, some of the stuff I got from some other resources. They're kind of mixed. So, yeah. Sorry. Alright. It's very, very important that you set your work out in an organized way. A lot of people don't do this. And they make this mistake and they're like, what the hell have I done? I've seen some people working out, and in chemistry especially, and they don't know what the hell's going on because they just get lost in your own working out. So what I would like to put on the side is N, C, and V. N represents moles, C represents concentration, V represents volume. Okay, sometimes you might not use all of it, sometimes you will, but we'll get started. Okay. 25 centimeters cubed of the solution of ethane dioic acid. So ethane dioic acid is this. I'm gonna write down 25 centimeters cubed. But every single time I'm talking about volume, I'm gonna convert it to decimeters cubed. How do I do that? I'm gonna divide by 1,000. If you put into your calculator, that should give you 0.025 decimeters cubed. Okay, and then we're just going to essentially fill in what the gaps that we have, and we'll worry about the calculations later on. We have 0.115, so I'm going to put down 0.115 here for my concentration. And it says aqueous sodium hydroxide solution was added from a burette, and 27 centimeters cubed was needed. So I'm going to put 0.02735 here in decimeters cubed. If you're unsure about which volume is talking about from a burette, sometimes it's a bit confusing. Just see what volume do you have already, so it means the other one must be that one. Okay, and we can already start to actually work out some numbers. Well, a good formula that we already know is what moles is the same thing as concentration times volume. Okay, and we can essentially just multiply these two to end up with the moles up here. So my calculator, what I'm going to do is times by 0.115 times by 0.02735, and that gives me 3.15 times 10 to the minus 3 moles. Now, using my molar ratio, I'm going to work out the moles of H2C2O4, and I'm just going to divide by 2 actually. 1 second, divide by 2, and that gives me 1.57 times 10 to the minus 3. Okay, now it says calculate the value of x in that. It's not really given it in the equation, unless I'm tripping. I mean, we can work out the concentration. I don't think we really need the concentration here. Let me have a look. Let me have a look if I'm missing some part of the question. Titrations. I don't even know where I got this question from actually. I might be completely off. But okay, let's work out the MR of this. The MR of this is going to be, I'll work out the MR, well, I'll give you the MRs for H, I'll give you the MRs for 12 for C, and the MR for O is 16. Can someone tell me what the MR would be in terms of X for this? And then we'll kind of use the moles to help us out a bit. The mass of water? Potentially. That's what I'm thinking. You can't calculate X from that. I'm thinking I'm just missing part of the question. I'm just gonna double check because it hasn't given X in terms of the equation itself. So it's like, what does it mean? I'm just gonna double check though and see if I can find the question again. 90. You get 90 in total. Is that 90 with 18? Yeah, perfect. Yeah, 90 plus 18x. Yeah, okay, that's perfect. It won't be 108x. Just double check that. Cool. Now that we've done that, we know that 90 plus 18x, I would argue, is, let me look at this again, is 25 equals, I can't work that out. I'm missing part of the question. That's what I'm saying. 18x has come from this water bit. I think I'm missing a part A. Because this is question 2. I think I'm missing a part A from this. Sorry guys. That's a bit sad. I don't even know where I got this from. Yeah. Oh well. Apologies about that. I don't think we can do the question. Just because we don't have the part A from it. I think the part A would have told us a bit more. And potentially it was just reacting with something else. And I can assume that we've done a lot of the work, by the way. I'll tell you where a lot of the marks will come from. This will be 1 mark from here. This will be another mark. And there's probably more information here. That's probably 2-3 marks. But yeah, sorry about that. Is it AS 2017? Is it? Oh my guy. My guy. One sec. Let me get this up. If it's AS, oh, you're a legend. Absolute legend. One sec. AS 2017. Question paper. Do you know what question it was? Enthalpy. because essentially I use a website that essentially just gives me those type of questions. Oh, I know it's not in 2017. Damn. Oh, is it paper 2? If it's not, if I can't find it, we'll move on because I've got plenty more. So don't worry. One sec. It looks really similar. Looks really similar. It's not 2017. I'll show you the 2017 one. You're talking this is the 2017 paper 2. It looks super similar. It's not the same though. Yeah, good memory though, man. Good memory. I rate that. It's not the same though. Sorry about that, guys. We'll move on. We'll go to the next question. I will come back to the script one. Okay, this one we can do though. This one we can 100% do. Okay, try this one. Use exactly the same thing. Make yourself the equation. Organize your working out exactly like this. Okay, it will make things a million times easier. Something called Dalton Maths. Dalton Chemistry, I think his name is. Dalton Maths or Dalton Chemistry? His name is Dalton. Dalton Chemistry. This one is, you can do an OCR, yeah. Like all the math stuff is like, other than time of flight, everything physical is, you can do an OCR and Excel. Yeah, of course. N, C, and V. N is going to be your moles, concentration is your concentration, volume is your volume. Set it out like that. You did it like this. Nice, BMZ. Spot the answer, bro. Spot the answer. I think it is one though. Let me check. I believe I put the mark scheme in the PowerPoint. Yeah, it is one. Yeah. So if you want to check, it is going to be one as your final answer. But yeah, we've already gone in 1 hour, which is interesting. We are 1/4 through the way. Let's see. I'll speed through this stuff. Inorganic will be quick though. I'm not going to spend a lot of time on inorganic. Inorganic is, I'm going to give you the equations for inorganic. You're going to screenshot them, write them down, whatever. That is your job to memorize them for tomorrow. No, Tuesday. Yes, Rico, how are you, man? How are you, my man? Is it redox titrations? Does this class as redox? This just classes as a normal titration, I'd say. This one will be redox. We've got redox one later on. Okay. Is it all the equations that you need to know? I've got a whole PDF. If you join my Discord, I've got a whole PDF for inorganic and organic actually. Should you revise prior to revising for bio paper 2? If you feel good for paper 1, then yeah. I'd say tomorrow, give you a day for paper 1 chem, and then after paper 1 chem, just spam paper 2. Okay, if you look in the description of my YouTube or Linktree if you're on TikTok, you can join my Discord from there. And there's a whole PDF that I've just put into the chemistry chat, and all the transition metal stuff as well, all the equations. Actually, in terms of the equations, it's there, but it's less. It's better if I teach it for equations because it's easier to understand that way. I should probably go and get my stuff up for this. Okay, let's start this. Always try and make yourself an equation that you can set out nicely. So you have hydrated sodium carbonate reacting with hydrochloric acid. What's that gonna make? Plus HCl. This will make sodium chloride. It will make carbon dioxide, and it will make water. Okay, then N, C, and V. We have a mass of this. Okay, we have a volume of our hydrochloric acid. I'm going to write that down straight away. Actually, wait. Well, this is going to be a reverse titration question. Ooh. Okay, so this is not a redox titration. This is a reverse titration. But I'm still going to write my stuff down. This is going to give me 0.2 here as my volume. So this is 0.2 decimeters cubed. I just did 200 divided by 1,000. And I'm also going to write down the concentration of my hydrochloric acid, which is 0.25. I can't really write down anything else at the moment. Technically, I can write down the moles, but I'm going to avoid that for now. Avoid doing that for now. I'm going to also write down another equation, which is here. It says several 25 centimeters cubed of the resultant solution were titrated with aqueous sodium hydroxide. Okay, so if you're reacting with sodium hydroxide, well, essentially what you have is your hydrochloric acid mixture reacting with sodium hydroxide. That's the only thing you can react with. You can only do acid and a base. You can't do a base and a base. So you're going to have HCl plus NaOH, and whatever that is, in terms of, you know, if it's a pure mixture, if it's an impure mixture, if there's like some mess in there, we're going to be using HCl as our reference. Can't find the PDF for the equation. Look on John. Look in the chemistry channel. Look on pin messages. It's in there. Okay, we have 25 centimeter portions of HCl. So I'm going to put this at 0.025. My concentration of sodium hydroxide is 0.15, and my titer is 26.6 centimeters. So I'm also going to convert that to decimeters cubed. Okay, Simon, if you look in the pinned messages in the chemistry channel, they are there. But if you scroll up as well, I've just put down the period 3 stuff as well, because the period 3 ones weren't in the PDF, but I've put them down. I've put them down if you just scroll up. Okay, but I'm gonna be going through those anyways today, so you don't need to worry. Okay, next we can start to work out some stuff. Well, we can work out the moles of sodium hydroxide. Sodium hydroxide moles will be 0.15 times by 0.0266. That's going to give me 3.99 times 10 to the minus 3. Also, while you're making your equation, make sure these equations are balanced. In this case, it's a nice 1-to-1 ratio. So just make sure they are balanced. That means that this must be 3.99 times 10 to the minus 3 moles here, with a 1-to-1 ratio. Now we can work out concentration if we really want, but we don't need to, because it says several 25 centimeter cube portions formed essentially this. Cool. Okay. Next, we need to figure out how many moles are actually in this HCl that we made. Let me just scroll back up. Yeah, how many moles do we have? So if we have 3.99 times 10 to the minus 3 here in 25 centimeters cubed, how many do we have in 200 centimeters cubed? Oh, I've kind of missed out a section here. But how many do we have in 250 centimeters cubed? Well, we have 3.99 times 10 to the minus 3 in 25 centimeters cubed. That means in 250 centimeters cubed, we're going to have 3.99 times 10 to the minus 2. Perfect. We just times by 10. Okay, so that means that in this part here, in the original 200 centimeters cubed, the reason why it's 200 centimeters cubed is because that's the original amount, and he just adds a bit of water to dilute it a bit to make it into this, but the moles doesn't change, so that's why it's still 3.99 times 10 to the minus 2. Okay. Now we need to check, is this equation balanced? I don't think it doesn't look balanced to me at all. Okay, so we have to be careful about that. So I'm just going to quickly balance this. There's 2 sodiums here, so I'm going to put a 2 here. That means that there are 2 chlorines. Oops, there are 2 chlorines here, so I'm going to put a big 2 here. And that is balanced. And I can put X here. That's balanced. No, that's not balanced. That should be fine. We'll leave it like that for now. Okay, because we will have some sort of H2O here that we can put a ratio in front of. But because of the 2 NAs and the 2 CLs, that's what we're more interested about. Okay, we'll worry about the CO2 and H2O later on if we need to. Okay, this part is what we're more focused on. That way, well, to work out this amount of moles, what do? We just divide the 3.99 times 10 to the minus 2 by 2. I got a ping in this code. Okay, and then divide this by 3.99 times 10 to the minus 2 divided by 2. That's going to give me 0.019 95. Ooh. .01995. Oh, no, we don't need to do that. The reason why we don't need to do that is because we've got this mass here. We're going to actually work out the moles of this and see how many moles we actually have. Now, when you do it in terms of molar ratios, you're assuming the fact that the whole thing completely reacts. In this case, it doesn't. We're given an original amount of mass in the beginning. Okay, so I'm going to work out how many moles do we have in the beginning. You're saying 0.05? Why do you say 0.05 moles? I mean, I do agree. I want to see your reasoning. Iman, why do you say 0.05 moles? I will also work out this 0.25 times by 0.2. Why do you say 0. Yes, exactly. You guys are right, 100%. So this part here, if we work out the moles, it is 0.05 moles. This part is what we have excess after doing this reaction. Absolutely right. So when we do the reaction here, 0.25 times by 0.2, this gives us 0.05. This number here is the excess of HCl, whatever's remaining, because the question says, after the reaction was complete, the resulting solution was transferred to a volumetric flask made up to 250 centimeters cubed. So we work that number here, which is just sitting here, I guess. And to work out the excess, how much is used up? Well, how much was used up was 0.05 minus this number. That's how much is used, and we get, Imad said earlier, 0.0101. But we have to be careful, since it's a 2-to-1 ratio, we have to divide this number by 2, because it's a 2-to-1 ratio here. So that means that this number of moles, if I put this into my calculator, 0.0101 divided by 2, that gives me 5.05 times 10 to the minus 3 moles here. Does that make sense? Does that make sense? Yes, you are allowed the CT50, 100%. For the guys on TikTok, your def is, I know it's a bit buggy, man. TikTok's always been like that. If you come to YouTube, yeah, I can say it again, 100%. I can say it again. So I'll restart this part. I'll keep this 3.99 times 10 to the minus 2. Give me a second. I'll restart this part. For the guys that are unsure. One second. Okay. So we worked out from our concentration here that we worked out 3.99 times 10 to the minus 3 for 25 centimeters cubed. The question says, after the reaction is complete, the resulting solution was transferred to a volumetric flask made up to 250 centimeters cubed. So this is the excess HCl. So after we've done some reaction, we have some HCl left over. We have some HCl left over in a test tube. Okay, we don't know the concentration of that. We don't know anything about that. So what we do with that number, what we do with that HCl, is we titrate it, and we find out that actually in this mini 25 centimeters cube sample, we have 3.99 times 10 to the minus 3 moles. But actually, wait, we had 250 centimeters cubed. So to work that out, we just times this by 10, and we end up with 3.99 times 10 to the minus 2 moles after the reaction has been done. Cool, so that's how much is remaining after your first reaction is done. In the beginning, we had 0.25 concentration and 200 centimeters cubed, this is in decimeters cubed, as your original reactant. And that means that if we just do N equals CV, that gives us 0.05 moles. I believe this is 100% in a past paper. I've seen it. I want to say 2019, but don't know. Honestly, I don't know. It's paper 1 question, 100%. Where was I? Okay. After this, well, we know that this is the excess amount. 3.99 times 10 to the minus 2 is the excess amount. This is the original amount. So how much is used? Well, how much is used must be 0.05 minus this number, which gives us 0.0101 moles. But wait, the equation is not balanced. We balance the equation to find out, okay, we have 2 sodiums. That means then this makes 2 chlorines. This must have a 2 HCl. If it's a 2-to-1 ratio, well, we're going to divide this by 2. And that gives us, in our calculator, 5.05 times 10 to the minus 3 moles. And that's how many moles must be in the beginning here. Does that make sense? Okay. Amazing, 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 amazing. Now that we know it's 5.05 times 10 to the minus 3 moles, we already have a mass in the beginning. We have 627 milligrams as your mass. We have our moles as 5.05 times 10 to the minus 3 moles. Okay. Using this, can you work out the MR? And using that, can you work out the value of X if our formula is Na2CO3.XH2O? Can you work out the value of X using this information? Okay, and once you've got that, just put the value of X in chat, and I'll confirm with you if you're good to go. What paper is this? I actually don't know. I'm gonna be honest, man. I'll put the link in chat already. If you check on PowerPoint, it's like all the questions that I've got that I'm planning on doing today. Whether I'll get it done or not, that's a different question. I will try to find out for you though. Can I go over practical errors? Nah. Potentially, maybe at the end if you have some time. I recommend you watch. Who should you watch for practicals? Kinda, there's not that many people good for practicals. I might be real, man. There's not many good videos. Yeah, listen, yeah. I have 89 slides. I don't know if I'm gonna get all those slides done. Yeah. We will do after this. We're doing a bit. What are we doing? A bit more. Oh yeah, I'm gonna go over the script that I've got, and then after that, there's one more redox titration. Or actually, I'm gonna go over this redox titration one. I'm gonna skip this one. I'll come back to that at the end, just because of time, and then I'm gonna go over Hess Law. That's probably what I'm gonna be doing. Yeah, more or less, HM. Yeah, more or less. You have generally 2 equations. Cool. X, you should get X as 1 for this. I'll quickly show you how to do it. The MR of sodium is 23. MR of carbon is 12. I think, is it 23 or 23.1? I can't remember off the top of my head. Oxygen is 16. H is 1. And that's it. How do I know HCl is in excess? It's because this is in 0.05. It's 0.05 is bigger than this number here. This number is 0.0399, which is smaller than 0.05. It's not necessarily in excess. Technically, yeah, it is in excess. We found out it's in excess. But generally, if you're trying to work out these type of concentrations, you'll find that your hydrochloric acid or whatever you're reacting it with is generally it's in excess. Your MR of sodium carbonate is going to be 46 plus 12 plus 48 plus 18x. That gives you, I'm just going to print my old calculator. It's too long to type the thing. 106 plus 18x. So you have N is equal to M over MR. We have moles, 5.05 times 10 to the minus 3. Sorry, it's a bit clipped on the top. Is equal to your mass, which is 0.627. Make sure you convert it into grams. And then your MR is 106 plus 18x. If you go ahead and rearrange for this, we should find that hopefully x is equal to 1. 0.627 divided by 5.05 times 10 to the minus 3. Okay, and then we're gonna minus 106 divided by 18, and x is 1.008, which is basically x is equal to 1. Calm. Alright, cool. For the guys on TikTok, yeah, tell all your friends to pattern and join the live right now. And tap the screen a bunch of times so more brothers join. Cool. I'm gonna do one more. For now, if you have some time, we'll come back. This question here, I think is really, really good. This is a redox titration, and there's some things I kind of want to go over before we continue this question. Actually, we'll start this question. And then some other things that I'm gonna quickly mention. Study circle. You feel drained. Honestly, it's a normal thing, and what you gotta do is just take a break. Honestly, take a break. If you feel like there's some stuff you like really like, I just can't do, then watch videos on them. But honestly, a break is very, very important. Downtime is equally as important as you revising, because what happens, right, when you do too much revision, I'm not saying don't revise, and you've probably seen on TikTok these brothers doing 10-hour revision, 12-hour revision straight. It's not it, bro. It's not it. When I was doing my revision, I was literally watching shows and I was doing past papers at the same time. But the reason why I could do that is, I don't want to bring anyone down here, but it's like, I started my revision quite early. Some people might start revision late, and that's why they're trying to find that they are cramming at the end. But either way, break time is very important. Downtime is very important. If you don't have that, you're going to burn out. Some people, they were predicted A's. This happened in 2023, actually. Some people were predicted A's, they got C's. That's what I'm saying, bro. Don't do the 13-hour revision, bro. Don't do that shit, man. Yeah, ask them at the end. Ask them what grades they got. Please. If they get A's and A stars, you're not fair, bro. Fair play, but they got no life, man. I'm gonna be real, bro. Go outside or something, bro. Go to the park, walk, do something. Alright, let me start this question. Whenever you see this phrase here, this phrase, half equation, this is a redox titration question. I started early in your high A's, we need A stars for you off. Where you apply? A stars, come on. You applied to Oxbridge, I know you applied to Oxbridge. You got Oxbridge offer, yeah, mashallah, man. That's sick. Man, that's sick. What is that, KCL? KCL, I know KCL, UCL, all those London unis. They want A stars. They want A stars. The northern unis, they don't care about A stars that much. You'll find that if you get an A, there's a chance you can still get in. It's Cambridge, mashallah, bro. That's sick. Mashallah, that's sick. Iman, yeah, I told you to touch grass, bro. Grass, smell it, bro. Touch the grass, feel the grass. See what you're losing out on. See what you're missing marks on. If it's just content, then get that content down. If it's exam technique, spam the same type of question over and over again. Okay. Hair bleach solution contains hydrogen peroxide. A sample of hair bleach solution is diluted with water. Okay. The concentration of hydrogen peroxide is diluted in the dilute solution is 5%. Okay, so it's very similar. So we're going to multiply up at some point. And then that 25 centimeter cubed of diluted hair solution is acidified with dilute sulfuric acid. And then we are going to titrate it with 0.02 moles of potassium permanganate solution. Okay. Whenever you see potassium permanganate, this is what you're going to write down straight away. Yes, you're going to write down MnO4 minus. This is your manganate ions. They go to Mn2+. You're going to write that down straight away. That's the first thing you're going to write. Anything to do with manganetes or potassium manganetes, you're going to write this down. Sometimes you'll see with iron. If you see iron 2 at any point, this is the first thing you need to write down. Fe2+ goes to Fe3+. If you see Fe3 plus, it goes to Fe2 plus. These two are linked. They're very linked, so be careful. And one more, this is really, really uncommon. This is AQA, yes, but it's going to be useful for OCR. Yes, it's recorded. If you hop onto my YouTube, it'll be uploaded there straight away. And one more thing, chromium. Chromium Cr2O7 2 minus goes to Cr3 plus. These ones, the chromium one is less common. I've seen it probably once, but these three are going to be your most common redox reaction ones. Okay, and actually potentially the hydrogen peroxide as well. Sometimes I've seen you might be expected to just make this type of equation, but it's going to be very uncommon. That's probably even more uncommon than the chromate ones. Those three are you need to know. Okay. Cool. I'm going to stick with the manganate. What we're going to do is balance this half equation out. And what we have is we have 4 oxygens on the left hand side. So how do we balance that? We're going to add 4 waters on the right hand side to introduce the oxygens. We can only add waters, we can only add electrons, and we can only add H plus ions. Well, we've added 8 H plus or 8 hydrogens on the right hand side. So I'm going to add 8 hydrogens or 8 H pluses on the left. No, Ria, no. They just expect you to know it. These are not in the data book. No. The only thing that's in the data booklet is your periodic table and your infrared spectroscopy stuff and the HNMR stuff. And in chemistry, in AQA, they add a bit of DNA stuff in there. Nothing else. Is pretty pointless, to be honest. The only useful thing is probably the HNMR and the IR spectroscopy. Okay, that's why inorganic is tough. This is a bit of inorganic technically. Yeah, it'll be uploaded after 7 since I'm finishing at 7. Now we need to balance the electrons. Well, the charge on the left hand side, this is a 7 plus. The charge on the right hand side is a 2 plus. We just kind of add all the charges together. Well, how do we balance the charges? How do we make them the same? We not necessarily make them for 5 pluses. We're not making the same in terms of like 0. We just make them the same in terms of whatever's the lowest one. So we're just going to add 5 electrons on the left hand side, which is just going to be a 2 plus now. Ria, they'll give you, for cell potentials, they'll give you in the question itself. They're not necessarily expecting you to memorize it. So yeah. Cool. Next, what we have is, well, we're going to combine these two equations together. So we've got this redox reaction. We've got this half equation here. We've got this half equation here. We're going to combine the two half equations together. And the way we do that is essentially just look at the electrons, and we're just going to balance the electrons. We've got 5 electrons here. We've got 2 electrons here. I'm going to rewrite this hydrogen peroxide equation on the bottom, like so. And then we'll just let's have a look. How can we balance it? I'm going to times the bottom equation by 5. I'm going to times the top equation by 2. But when we need to make the equation, what do we need to keep in mind? You need to keep in mind in terms of what the manganate ions go to. So MnO4 always goes to Mn2 plus. Fe2 plus always goes to Fe3 plus. Fe3 plus always goes to Fe2 plus, and chromate ions goes to 3 plus. Okay, I'll write that down afterwards after we do this question again. Okay, Hasnain. Okay, let's combine the two equations together. So the top equation will go to 10 electrons. We'll go to 16 hydrogen H pluses. We'll go to 2 MnO4s. On the bottom, we'll have 5 hydrogen peroxides, and this will go to 2 Mn2 plus, 8 waters, 5 oxygens, 10 H pluses, and the electrons actually end up cancelling out, so I'm not even going to bother writing the electrons. Cool? We've just combined the two equations together. I've times the top one by 2, I've times the bottom one by 5, and I've added the reactions together, I've added the products together. That's all I've done. Next, I'm going to see what do I have on both sides of the equation. Well, I have H pluses on both sides of the equation, so I'm just going to remove the excess. So this just becomes 6. Let me check if I've done that right. Yes, so I have 10 hydrogen H pluses on the right, 16 on the left. 16 minus 10 gives me 6. Are we happy with that? Yep, nope. Any questions on that? Any questions on what I did from the start part to get here? Cool. Amazing. I'm taking that as we're all good. Alright. Next, what we're going to do, I'm going to clean this up a bit. Let me write this a bit more nicely. Cool. Okay, now it's just a simple titration, I can't lie. It's actually a simple titration. Yeah, go for it, bro. Rico, go for it, man. Now what we're going to do is we're going to sub in all the kind of information that we did, that we had before. So on the side, again, N, C, V. Okay, N, C, and V. Yes, Amira, I'll explain it again. Give me a sec. And what we have is we have acidified sample. The acidified sample is titrated with 0.02. So I'm going to put 0.02 here as my concentration. My volume of the diluted bleach solution is going to be my my hydrogen peroxide, and that's going to be 25 centimeters cubed. But we also have to remember at the end we just have to convert that back to 100% since it's diluted to 5%. So just keep that in mind. So at the moment it's 25 centimeters cubed in deciliters cubed. Okay, the sulfuric acid is actually the 6H plus here. That's what the 6H plus represents. Okay, and it also says the reaction is complete when we have 35.85 of the potassium permanganate solution. So I'm just going to convert that to here. Now what the question is asking is, we've given the ionic equation. That's done. We need to work out the concentration of the hydrogen peroxide in the original Hess solution. So we're just going to use some of our just basic calculations to work out what the concentration would be in 5%, and then we'll times it up to work out the 100%. So what we'll have is the following. We're going to work out the amount of moles here first. So what we'll do is, let me pull up the calculator. We're going to do 0.02 times by 0.03585. Sorry, that my handwriting is a bit bad there. And we should end up with 7.17 times 10 to the minus 4. If I've done anything wrong, please just let me know. Cool. And then I'm going to do my ratio. How do I go from 2 to 5? There's multiple ways of doing it, but you can just times by 2.5. You can divide by 2 times by 5. That also works. I'm going to times this by 2.5. And that gives me 1.7925 times 10 to the minus 3. 7925 times 10 to the minus 3. And that gives me that amount of moles for hydrogen peroxide on my bleach solution. To work out the concentration, I know that concentration is moles is equal to concentration times volume. So moles divided by volume gives me concentration. So I'm going to divide this by 0.025, and that gives me 0.0717. But remember, if you go back to the question, this is only 5%. 0.0717 is 5%. So what's going to be 100%? What do we get as that final concentration? You can still use this. This is still for OCR. It's still completely valuable for OCR. It doesn't have to be AQA. This reverse titration stuff. This is completely fine for OCR and Edexcel. But if this is 5%, what do? We're going to times by 20 to get to 100%. And we should find that it's going to be 1.434 or 1.43 moles per decimeter cubed. That is going to be your final answer. Okay. I'm going to quickly recap what we did. The hard part was not this, in my opinion. I think this was actually the easy part. The hard part is probably making the equations itself. For the guys that have just joined, remember that your manganate ions will always go to Mn2+, and then balance it using your redox rules. Iron 2+ goes to iron 3+. Iron 3+ always goes to iron 2+, and obviously balance in terms of electrons as such. And chromate ions as well. This is a rarer, but it can still come up. We'll go to chromium 3+ ions. These ones you need to know by heart. Okay, and then balance, then balance, obviously. Okay. Cool. And then essentially what we did as well after that, we combined it with the hydrogen peroxide. So you got half equation, just like you do in terms of electrodes. Make up the electrons to the same amount, and then combine, and then get rid of any excess stuff that you don't want. Okay, amazing. Cool. Let me pull up the next stuff. I think we'll move on to Hess Law. Let's move on to Hess Law. Hess Law is not a very big topic. I think it's a really, really nice, chill topic. We'll keep it simple. It's not too bad. And then we'll look at Born-Haber cycles, which is also a pretty simple topic, in my opinion. And then after that, I believe it is Group 7. Okay. we have two types of enthalpy stuff that you're going to be using for your Hess Law. That's going to be enthalpy of combustion and enthalpy of formation. So enthalpy of combustion essentially is when you're reacting it with oxygen. So this reaction up here is the enthalpy of combustion itself. If you're unsure which type of arrows you're going to be thinking about, just look at your table. Your table will tell you which one you're going to be using. In this case, we're going to be using our formation arrows, which is going to be upwards. This is how I remember it. F is tall, so the arrow is going up, and combustion is short, so the arrow is going down. That's how I kind of remember it. But the formation arrows are going up, the combustion arrows will be going down, and the one you're going to be using is going to be the one in the table. Okay, so I'm going to rewrite the equation that we have already here. C7H16 plus 11O2 goes to 7 carbon dioxides and 8 waters. We have the up arrow, so I'm going to put the up arrow here. Now, since it's a formation, I'm going to put my formation elements on the bottom. You don't actually get marks for this, so you don't have to, but I think it's a good habit to get into. We have carbon, we have hydrogen, and we have oxygen. I'm going to balance them, and I have 7 carbons here, so I'm going to put big 7. I have 16 hydrogen, so I'm going to put 8 here, and I also have 11 O2s, which is just going to be 11. Okay, remember, can you do products minus reactions? Not in this, because this is Hess Law. But yeah, Dom, you are right. Yes, you're right about that. Products minus reactants is generally for, generally it is, Imran. Yes, it is. For combustion, it's reactants minus products. But for Hess Law, it doesn't apply in this sense. You need to do something else. Okay. Now, remember that when you have, in terms of your formation, you can see that we have 11 oxygens here and we have 11 oxygens here. There is no enthalpy change from oxygen to oxygen because they're exactly the same. Just keep that in mind. What do I mean? It just is when you're working out like delta H. Do you have to draw the Hess cycle? You don't have to. You don't actually get marks for the Hess cycle. I think it's nicer to. If you're able to do it without, great. If you need it to kind of figure it out, that also helps. I'm showing you how I would do Hess Law, and I think it works every single time. And I'm going to show you how to do Hess Law in a second. There's no formulas or anything like that. So what I'm going to actually put down first is just the numbers. That's the first thing I'm actually going to put down. The enthalpy of combustion is going to be just a forwards reaction. It's just your reactants reacting with your oxygen. So this is going to be minus 4811. Cool. Now your enthalpy of formation to make carbon dioxide, we've already got in our table. Well, this is per mole, so we're going to do 7 times by minus 394. And then waters, we have plus 8 waters, so we're going to have 8 of our minus 286. Okay, whatever that number is, I don't know off the top of my head. Let me just rewrite this real quick. Okay, now the question's asking us, what is the formation? It doesn't really say, to be honest, but it'll be asking, what is the formation of our heptane here? You've got minus 235, essentially. I don't actually have the answer on me right now, but I'll show you how to do this real quick. So, the enthalpy of formation in this case, this is what I call the arrow method. Essentially, you follow the arrows. So, we need to work out what is the enthalpy of formation, so we need to work out what this upwards arrow is. Well, the definition of a Hess's law is that the energy or the enthalpy is exactly the same, which is independent of the route taken. Essentially, it means that no matter which route you take, it will give you the same answer either way. Meaning, well, we need to work out upwards. What other way can we figure out how to go up? Is we go up here and then we go left. Okay, so upwards in our calculator, if we put this into our calculator, we can find that it's going to be 7 times by minus 394 plus 8 minus 286. So this number here is going to be minus 4046. Okay, going up, I'm going to clear this out. It's minus 4046. But since we said we had to go left, we're going to swap the arrow. So if going right is minus 4811, going left will be positive 4811. And that will give you, if I add plus 4811, and that should give you minus 235 as your final answer. Counterclockwise equals anti-clockwise arrows. That is essentially the same thing. I don't know if that will work every single time, Simon, though. Because, for example, if you're trying to work out the one on the top here, sometimes, but you don't really have an anti-clockwise arrow there. Like, I get what you mean in terms of anti-clockwise here and here on the left and the right, but on the top it might not work. So that's why I really like the follow the arrows method, and reason being it works on your Born-Haber cycles as well. Okay, it feels like you guys are quite confident on Born-Haber cycles, so I might actually skip past this topic. That means you can just speed ahead. But if you're feeling unsure, definitely just let me know. Okay, I'm gonna speed ahead. No, not feeling confident. Oh shit! Alright, let's do another then. Nah, you will. Why not? You don't get. It's a 2 marker. I'll tell you where you get the marks from. You get the marks from minus 4046, and you get the mark for the final answer. You don't get the marks at all for drawing the Hess Law at all, BMZ. It depends. If it's even with enthalpy of solution, you don't need to. As long as you're writing, well, for example, I haven't really shown like in terms of calculation here, but if you're showing the calculation here, minus 394 plus 8 minus 286, and if you've shown that there's minus 4046, and if you've added, that makes this. In chemistry is very lenient in terms of your maths. You'll get full marks actually. If you put the answer down, you'll get full marks. In your 5 markers up here, if I go back to the time of flight question, if you put the answer down straight away, I don't actually have it here, let me go back to the PowerPoint. If you put the answer down straight away in the PowerPoint here for your time of flight questions, without any working out, you get full marks. That's how AQA works. And if it's the correct answer. If it's the wrong answer, you're not getting any marks, bro. It's weird in terms of its mark scheme. Like sometimes it gives carry through, sometimes it doesn't, which is a bit annoying. But to be fair, it's better than biology, so at least that's all right. Okay, enthalpy of combustion and enthalpy of formation definitions. These are good 2 markers that I think. Can I go to the method question on the PowerPoint? Which method question? Method question? Tell me what slide, M. It should be minus. It's because you have minus 4046, and then you're going up, and then you're going left. So this causes this to become positive. What you worked out, Al, what you worked out is a downwards. That's not the formation. The formation is from your constituent elements to the molecule here. Okay, so your formation needs to be going upwards. Yeah, we're gonna be doing Born-Haber cycle afterwards. Tell me what slide, M, and then I'll look at that afterwards. Definitions are very important. I think they're good. They're good marks. Propane 2O undergoes combustion when it's ignited. Kind of irrelevant to the question. Define the standard enthalpy of combustion. Slide 13. Oh yes, I completely forgot about this. Oh, thank you for reminding me. Oh, yes. I needed to do this. Yeah, 100%. I will actually put that on right after that. Thank you so much for reminding me about this one. Yeah, 100%. This is very important. Okay, we'll do this one afterwards. Okay, standard enthalpy of combustion. You're gonna write the following. Oops, my pen. Enthalpy of a reactant, specifically 1 mole of a reactant, reacting with excess oxygen. Yeah, perfect, Farah, perfect. Full marks. With all reactants and products in standard states. In standard states and conditions. Perfect. Bang on. Absolutely bang on. Can you also tell me then the definition of enthalpy of formation? enthalpy of formation. Perfect. Perfect, M. Full marks. Appreciate it, Ams. Appreciate it, my guy. Let me see how TikTok's going. What, physics? Yeah, I can't. Is it physics tomorrow? Is it physics paper 2 tomorrow? Or paper. Is it paper 1 or paper 2? I think it's paper 2. Enthalpy change when 1 mole of a substance is formed from its constituent elements with all reactants, products, and standard. Yeah, perfect. Perfect. Bang on. Absolutely amazing. I'm going to literally copy this and I'm going to put it on screen for the guys. Absolutely bang on. Enthalpy change when one mole of a compound is formed from its elements with all reactants and products in the standard states under standard conditions. I'm going to put constituent. That just means it's the same thing. You don't have to put that word there, but this is going to give you full marks. Amazing, everyone. Bang on. Cool, cool, cool. That's going to be the definition of formation, and that's a really, really nice 2 mark. Cool. Let's look at this script here. This script is a very lovely script. I think it's nice. I'm going to give you exactly the terminology you need to just get full marks on this. Okay. It says the student needs to make an aqueous solution up to 250 centimeters cubed of just any mass. It can be an acid, it can be sodium hydroxide, doesn't matter. Essentially what you're doing is you're making a standard solution of this. Okay, and this is your standard solution practical. And I'll give you the exact words that you're going to need to write this down. First thing what you're going to do, I know it's a beautiful question. First thing what you're going to do is you're going to get your balance and you're going to set it to 0. So electric balance and set it to 0. Okay, you can, if you don't include this part here, actually, if you don't include this, actually no, I'm gonna, you know what, avoid this part. Get the electric balance. The reason being, this is more mark scheme, so I'm gonna tell you from mark scheme directly. You have an electric balance. Then what you're gonna do is you're gonna put a weigh bolt on the balance and measure out. I would say when you measure out stuff, yeah, 100% M. Measure out a mass. Just pick a number. Okay, 10 grams, 5 grams, whatever. Just say. Don't say measure out a mass. Just pick a number. So measure out 5 grams. And if it says in terms of calculations, because I know OCR does a lot more in terms of, in comparison to AQA. If it gives you, like, for example, you want to work out a specific concentration, do the calculation first, and then put down what mass you need. Okay. Let's say, but in this case, it's not really giving us anything, so that's fine. Measure out 5 grams of MHCl3, okay, and with a spatula, cool, and place on boat. Then what you're going to do is you're going to pour the mass into a beaker and reweigh the weigh bolt. Now the reason we reweigh the weigh bolt is essentially we're gonna subtract the mass of the weigh bolt. I know you can just click 0 on the scale, and if you did do that, if you did put that in your mark scheme, in your answer, you probably would still get full marks. But I've seen sometimes in terms of a like a practical type of question, Farah, not really. Sometimes they'll just make up a number. It doesn't matter. Okay, if it tells you if it tells you in terms of concentrations, I'll get to the volumetric flask in a bit. Not yet. There's no volumetric flask yet. Yeah, you can say weighing by difference, but the reason why I'm saying reweigh the weigh bolt is because I've seen it in terms of a practical thing. If you said set it to 0, that's fine. But in terms of a practical question, I've seen it and they've left like a gap and they've literally put, so the answer is reweigh the weigh bolt. The whole point is you can set it, you can subtract it from the original mass. That's the whole point of it. And the reason why I'm telling you now in terms of like the 6 marker is just directly from the mark scheme itself. You get me? Okay. But there's more than one answer. If you set the balance to 0, that's fine. You don't have to say how many grams. Was it for olive oil? I think so, maybe. If you know what I'm talking about, then that's great. But yeah, cool. Once you reweighed the weigh bolt, cool, that's perfect. What we're gonna do is add distilled water. to the beaker and stir with glass rod. Always try and mention your equipment as much as you can until dissolved. Cool. I'm going to slightly zoom out for the guys that can't see. Cool. Until dissolved. Then add solution to, make sure you say the mass, or sorry, the volume of the volumetric flask. 250 centimeters cubed. I'm going to underline this. Volumetric flask with a funnel. Okay. Then we're going to add distilled water. We're going to add even more distilled water until the graduation mark, or you can say the line, but it's called the graduation mark. To the graduation mark. That just means that the point of the 250 centimeters cubed. Yeah, you can use tea pipette. That's honestly, you don't need it in terms of the mark scheme, but I think it's good to have the pipette thing. Yes, we do need to add the washings as well. Actually that should probably be before that actually. Add washings to flask. Then you add distilled water to the graduation mark. Take off the funnel. I would say this is actually a decent point as well. Not all mark schemes will have this. Sometimes they will. The reason why we take off the funnel is because, so washings essentially is all your equipment. You just add a bit of distilled water. So you just, anything that's remaining on your equipment, maybe on the glass rod, your beaker, and that's called the washing. You just add it to the funnel, to the flask. Okay, take off your funnel, and then you're gonna shake or you invert. This is a very, very important last marking point, and a lot of people actually miss this. Shake / invert the volumetric flask. Okay. The reason why we do this is, how do I remember this? I don't know, man. Honestly, I don't know. I did this last year, bro. I did chemistry last year. To be fair, I teach chemistry, so you know what, I'm quite on top of it. This is AQA stuff, but it's very, very helpful for EDXA and OCR. This is actually helpful for OCR actually. You can use this exact script for OCR. But that's your 4-6 marker. It's probably actually more, depends on the 6 marker itself. But yeah. Exactly, yes, exactly, HM. Beautiful term, homogeneous. That's exactly why. It's so you don't have areas with less concentration, areas with more concentration. It makes the solution equal, or the actual word is homogeneous. Yes, Jacob. It is making a standard solution script. Okay. Beautiful. It covers all of it, to be honest. In terms of reasoning, I'll also put down the reasoning in terms of why you take off the funnel. So extra drops don't affect the volume. Sometimes there might be a 1 marker on this. It's just a reasoning. In terms of why do you reweigh the weigh boat, so you can take account of the mass correctly. That's essentially what that means. Graduation mark. Sorry. Graduation mark. Graduation point. The 250 centimeter line. Anything like that. That just means that. Okay. Not really. It's because you're not really looking at in terms of the. You don't have to be specific with meniscus. It's not like necessarily a measuring cylinder. That's what I'm talking about. Yeah, Jeremy. Exactly. That's what I've said. So extra drops don't affect. It's better if you do it because it's just talking about a 6 marker and how you make it. You don't need to talk about why. Why am I doing econ in terms of dentistry? Plans changed. I did talk about this earlier. I didn't get through my interviews last year, so this year I was going to reapply. Then I just thought about it. I was like, do I really want to do dentistry for 5 years? And then I just changed it to econ. But yeah. Yes, I'm going to be doing transition metal stuff as well. To be fair, we're pushing 2 hours. It's 5 o'clock almost, so I will be doing the inorganic stuff a bit more now. Cool. Next part. Oh, should we do a bit more Hess Law? Let's do 2 more Hess Law, and then we're gonna start Born Haber, and then we're gonna do Group 7. We'll do that. Okay, that's 1 Hess Law, 2 Hess Law, and then we'll move on to Born-Haber cycles. Enthalpy change of combustion for alcohol J. Have a go on this. If you can answer for this, great. If you don't worry. I guess we'll go through it. This is HF, by the way. Use what I've just told you. Yeah, guys on TikTok, if you guys want to come onto YouTube, because I'm looking more on the YouTube stuff. If you guys are more interested, just come to YouTube. Yeah, just come to the link in my bio, and yeah, it was a good eat. Yeah, it was good. It was good. How was yours, Simon? Can't lie though, I had listen in the morning. I woke up at I woke up at a decent time, but I slept late. I was working on the course last night. I was like, yeah, I need to get this done. So I slept a bit late. Yeah, but the guys on TikTok, yeah, come onto YouTube. Go on the link in my bio, bro. Yeah, fair. I can't let everyone's doing revision. There was exams for GCSEs on Friday. So fair. You were thinking about doing PPE, but you already applied to uni. I see. See how it goes. I think honestly, I mean, if it's Cambridge is quite strict with it. I'm not gonna lie, they are strict. Ria, there's no link. There should be a link tree. If there's no link tree, then I don't know what it is. It's glitched for some people, because some people said there's a link, and then some people have just come directly from TikTok, and then some people can't see the link at all. There's a link tree. Click the link tree. If there's not, then it's alright. If you look on YouTube, though. Alright, we got -3320. We got one number. If you just search Study Sphere tutors, it should just come up. Real. Okay. No, it's fine. No, I've got it. No, not on TikTok show. Not on TikTok show. On my bio. I'm over 18 though. I'm over. But do I look under 18? I verified my thing though. It was asking me the other day. I verified it. It's taking the piss, but I did end up verifying it. Alright, first bit. Let me quickly do the first bit. We've got standard enthalpy of formation. So we have carbon plus hydrogen plus oxygen. That's pretty simple, and just make sure they have the right state symbols. So if this is a liquid alcohol, so I'm going to put this as liquid. This is going to be a solid for your carbon. It's going to be a gas for your hydrogen. It's also going to be a gas for your oxygen here. I'm actually going to rewrite this on the side because it's really messy here. Carbon plus hydrogen plus oxygen makes C5H12O, and your state symbols are needed. If you don't put state symbols, you've got it wrong. No mark. Okay, so remember that. Okay, we need to balance out the numbers. Well, the number in front of the O is just, I'm going to put half here. In front of the H2, I'm going to put 6, and then I'm just going to put 5 in front of the carbons. Okay, fair enough, Usman. Yes, it will be uploaded later on. I got an A-star. I got an A-star at chemistry. Cool. Next, I'm going to rewrite the equation here. H12O. Sorry, C5H12O plus 7.5 oxygen makes 5 CO2 plus 6 H2O. And having this equation is useful, so I'm just going to bring this down. I'm going to put arrows up like so. Now, why have I put arrows up? Because it's formation in the table. And then what we're essentially working out is this number here. So this is going to be our question mark. What exam board is this? This is AQA, but this is useful in Edexcel. I don't really think you look at Hess Law much in OCR A2 anyways. You probably look at it a bit in A1. Not A1, AS. Cool, we guys are getting -3320. Muhammad, just check. You got 3034. Just give a double check on that. I don't know if you might be actually right, and the other guys might be wrong. So I'll have a look. You're going to be doing it right now. Well, the formation to make our alcohol is going to be -366. Did I do something wrong here? Did I do something wrong? Am I tripping? Oh, I forgot about the water. No. Oh yeah, okay. There should be 7.5 anyways. So I'm gonna put. Okay, yeah, I understand. So the reason why it's 7.5 here oxygens is because it's just oxygen here. It just transfers over. It doesn't really matter. Is it not products taking reactants? The reason why is, you can think of it like that. I guess you can think of it like that. It depends. It depends on the question itself. But with Hess's law, you have to be careful how you treat it. If you get the same answer, then fair. If that method works, then fair enough. 5 times that minus 394. Why? Because we have 5 moles of carbon dioxide. We have 6 waters, so we have plus 6 minus 286. And I'm going to add this together. And this gives me the following. 5 times by minus 394 plus 6 times by minus 286. And that gives me minus 3686. I'm going to get rid of this and put this here. Minus 3686. And I'm trying to work out this direction here. Sorry, is it 802? Oh yes, sorry. Absolutely right, 802. But to be fair, I don't think I'll lose marks for that, which is alright. It doesn't really matter. Yeah, we don't need it. Yeah. Okay, cool. We're trying to work out in this direction here. We're trying to work out this arrow. Well, what other way can we do? Well, we can go down, and then we can go back up. Well, if we've gone down, we have to switch the arrow. So I'm going to add 366, and then I'm going to follow the same direction anyways. So I'm going to do 366 minus 3686, and this gives me the following. In the calculator, 366 minus 3686 minus 3320 should be your final answer. Kilojoules per mole. Cool? Nice? Any questions on that? Follow the arrows. Okay, follow the arrows. We're not using no equations. My teacher, honestly, he was really good. But yeah. Alright, see you later, M, man. Take care. Take care. Why is the arrows going up? The arrows are going up because there is formation. The arrows are going up because of the formation. Look in your table. Okay, if you look in your table, it will tell you which it is. Formation is going up. Combustion going down. Now I'm not doing anything tomorrow. I'm staying on until 7 anyways. If you want to come back later on, we'll be doing something then. Alright. Cool. Let's continue on. I'm going to go to Born-Haber cycles. We're going to do like 1 or 2 for Born-Haber. And then I'm going to go to group 7 and the inorganic stuff. Yeah, 100%. It's going to be rewatchable, 100%. Okay. Let's look at some Born-Haber cycle stuff. When we're having a break. Good question, man. There's no breaks. You guys want a break? We can have a break. If you guys want a 10-minute break, you know what? Let's have a 10-minute break. Why not? Let's have a 10-minute break. We'll come back at 5 o'clock. That's 7 minutes. I know it's not a lot, but it's a 4-hour session. You guys can rewatch this back anyways. So you guys can have a break. Yeah, order Pepe is just eat and chill, bro. I'm gonna be teaching either way, bro. Yeah, I'll have a 2-minute break. Am I doing another maths one? I'll have to see. Man. I might do in terms of applied. What am I doing right now? So after Born-Haber cycles, we're gonna be doing group 7 and group 3. I'm gonna go through group 7 period 3 and group 2 quite quick. Just because it's just stuff that you have to memorize. I'm not really gonna explain it that much. Just because it's just memorization that you have to do. Catalyst equations, I'm also just going to be doing, it's just going to be a memorization thing. Transition metals, I'm actually going to try to go in depth. And acids and bases as well. I'm going to try and go in depth. That's going to be the main focus for the rest of the hours. With enthalpy of solution. I'll show you how to do this. That's the thing. The way you do it. It applies in every single one. Okay. We'll take a little break though. If you want to do something, we'll until 5 o'clock. I don't know. We can just chat. We can just chill. If you want to go get some food, go get some food. But yeah, have I done the whole paper one today? Not yet, but maybe. Yeah. Probably won't be everything. There's electrodes. I don't think we'll be able to do electrodes today. I know there's like, you know, average isotope stuff. We looked at that very briefly. That kind of stuff. I'm trying my best because there's a lot of topics. It's physical and inorganic. That's literally 2/3 of the whole spec in 4 hours. Yes, Army is being. It'll get uploaded directly. It will get uploaded directly onto YouTube. Come to my YouTube, Study Speech Users. I'll put this in chat. Give me a second. For the guys on TikTok. Look on that on YouTube, and you'll find it. Okay. Maths finished you off. Was the maths paper not good? I looked at it, it was decent, man. But you have paper 2 to clutch. Clutch on your paper 2. Yo, I don't know how the brothers revise for 10 hours a day, man. I can't do that, honestly. I'm dead after 2 hours. But you guys gonna cook, bro. You're gonna do electro percentages for real. You be real. I'll see. I will. You know what it is, bro? Screw electrodes, bro. Leave electrodes, man. Let me pattern you up on inorganic first. Let me pattern you on that first. Then we look at electrodes. What's bio? If I'm bio calm, some people say it's calm. Some people say it's hard, bro. 14 hours, crazy, bro. I can't lie that, bro. That's it. 14 hours, bro. It's actual propaganda. I'm telling you, it's propaganda. Bro, I wish I could turn on my camera for TikTok. I can't have my camera on in 2 places at the same time. So, you guys tap the screen on TikTok though. If you guys on screen on TikTok, just tap the screen. Do we need to know enthalpy of atomization, ionization energy? Definitions. I'm gonna say. Like the inside out, I'm going to say no. Yes, I'm going to say no. AQA asks more about definitions. In terms of like the meaning behind it and how it interacts with your Born-Haber cycles, yes. Like you got to know what enthalpy of atomization is. You can't, if you don't know what it is, you can't access Born-Haber cycle questions. And so definition questions, they're a lot less common, but they can still pop up. How was OCR bio? Just tap the screen, bro. Yeah, man. Appreciate it. Yeah, to be fair, it's actually cut off. I just joined now. You know how to do my Born-Haber, but I don't know the full definition. Okay, I mean, I'll go through the definitions as well. Like, I'll kind of explain it at the same time. Yeah. No, that's fine. That's fine. We'll start again at 5 o'clock. We'll start again. So yeah. What do you do when you got your bond enthalpy value? What do you mean? You just chill, bro. That's your answer now. When you bond enthalpy value. In a Born-Haber cycle. Oh, if you get bond enthalpy in a Born-Haber. Good question. You're going to be using that in terms of your... it'll probably be to do with the atomization or bond dissociation. So, for example, I'll give an example now. Let's say the bond enthalpy of chlorine to chlorine, bond enthalpy is, let's say it's 186, right? Let's say it's 186. Well, to break it is 186 kilojoules per mole. Because that's going to be essentially your enthalpy of atomization. Okay, so enthalpy of atomization is essentially you make chlorine like so from a half Cl2. That's your enthalpy of atomization. So this is actually going to be 186 divided by 2 technically. But in this case, you see that this is going to be 121. So you're going to be timesing this by 2. This will be Cl2 makes 2Cl. That makes sense? Yeah. I'm going to LSE economics. I did maths for maths, chemistry, and biology. You're learning this in year 12. That's good, man. That's good. That you're learning it in year 12. It's a good place to be. I think thermodynamics is really, really good. Oh yeah, and like I think someone was asking me what we're doing in terms of paper 1. I'm not doing Gibbs today. And rates, I know rates comes up in paper 1 or CR, I believe. I know it's in physical, we're not looking at rates. But yeah, appreciate it, guys, thanks. But yes, it's a change from dentistry. The original plan was dentistry for the guys that know me, or the OG guys. Yeah, that was last year. As of today, yes, right at the end. We're going to be looking at pH curves, briefly-ish, and then buffers, and some of the buffer calculations. Like, I know there's a question where there's like, if you have a buffer and then you add an acid or a base to it, something happens to the pH. In OCR, you don't even look at that really. It can still come up technically, but in AQA, I've seen it happen multiple times. Why did I change from dentistry? Is I didn't get in the first time because of my interviews. So I got all my interviews actually, but I just didn't get through my interview stages. Again, the guys that know, Sheffield gave me an offer, but then they took it back because it was a mistake. I have the email somewhere, but I don't know where they are. I lost my access to my school account. But yeah, so I was gonna reapply this year, well, last October, and I just didn't apply. I was like, yeah, I'm not doing dentistry anymore. My guy sharing the live, my guy, appreciate it, bro, appreciate it. But yeah, mental law, that's very nice. What are you doing law at? But yeah, man, it's a change. I think I'm more business minded. But like equally, I'm still teaching maths now. I'm still teaching chemistry now. I'm still going to be teaching in probably like next year, probably the year after still. I enjoy it. I do enjoy teaching. Like, I'm not making any money from this. You guys are here. I'm just chilling. Like, this is completely free, bro. So yeah, man. All the videos, all the live sessions. I haven't made a single penny. Just something I enjoy, man. It was. But you know what? LSE economics is very maths based as well, which I'm happy about. I don't regret it. Everything I did last year, I don't regret it. You gotta live without regrets, man. But it is what it is, bro. But LSE took a really, really long time this year. You're given bond dissociation of oxygen. Do you have it? It depends on the question. So if it was at half O2, so if it was like a half O2 up here, then you would. But bond dissociation is just O2 to 2O. Bond dissociation is 1 mole in your reactants. Atomization is 1 mole in your products. That's the difference. You guys can't really see that. Oops. So this is atomization. This is bond dissociation. You don't need to know about bond dissociation for OCR, by the way. But that's just a differentiation between them. Okay. Cool, that makes sense, Ams. But you know what it is? That's kind of like the... yeah, I can see your comments. on TikTok. I mean, this guy's sharing quite a bit. I mean, fair enough, innit? My guy, Fahad. Yeah, he's kind of spamming the share. I mean, fair enough, bro. I appreciate the share, but I'm not joining. No one's joining, bro. He's sharing. No one's joining, though. It's alright, though. I appreciate the sharing. Cool. You know what? Let's start again. It's 5:03. Let's start again. Okay. Okay. Yeah, put my phone on the... I don't know where to put my phone. My desk is so packed. Alright. The first thing we're going to do is fill in this table here. So if you've already kind of drawn the table, that's nice. If you haven't, then I guess kind of follow along. We want to finish this Born-Haber cycle. So you can see that this calcium and this chlorine is going to be our formation. Okay. Then after that, what we need to do is just look at what's happening in terms of this next stage. Well, at the moment, let me just look at this. It needs to be atomized. Our calcium needs to turn into a gas somehow. And the way it turns into gas is going to be through the enthalpy of atomization. That's going to be our next step, like so. Cool. Then you can see it gets ionized. That's the first ionization energy. This is going to be the second ionization energy. And if you feel like, okay, which ones haven't I used and which ones have I used, you can actually kind of tick across sort of enthalpy of atomization, first energy. We haven't done atomization of chlorine yet. We haven't done affinity yet. We've done formation, and not this one yet. Why is there a plus on Ca? I don't know. I don't know why there's a plus. Yeah, you're right. You're right. It's atomization. I don't know why there's a plus there. You're right. No, you guys are right. You're right. You're right. Cool. Next, we're going to do atomization on chlorine. Well, a chlorine atomization definition is when you have 1 mole of a gas made. Okay, but we have Cl2. We don't have a half Cl2, so we're going to be timesing by 2. Okay, so if our atomization is 1 to 1, we're going to times that by 2. That's going to be 2, 4, 2. Okay, so that will essentially become calcium 2 plus 2 electrons plus 2 Cl gas. Amazing. This is going to be our electron affinity because each of our gaseous chlorine molecules gains an electron, and then this is going to be our lattice formation. Now what I like to do is actually just put the numbers across on each side, or on each of the lines. So we have atomization of calcium, which is going to be 19, I'm going to put 193 here. First ionization of calcium is going to be 590, so I'm going to put that here. Atomization of chlorine, we already worked that out, it's 121 times by 2. Electron affinity of chlorine, well, we have 2 chlorines gaining 2 electrons, that's 2 of the affinity, so I'm going to do minus 364 times 2. And you'll actually notice, why does a chlorine have a charge on the top? No, it does not. Not yet. When it's atomized, this is atomization, it doesn't. When it gains the electrons, it does. I know sometimes you've seen chlorines have charges on the top, sometimes it does. It's not all, it doesn't happen all the time. You kind of have to base it on the question itself. Okay? The arrows going down are going to be negative. The arrows going up are going to be positive. Just remember that, okay? The enthalpy is, we just did this. The enthalpy of formation is minus 795. So this downwards arrow is minus 795. Okay, and we also have this other downwards arrow, which we have is minus 2237. What we are trying to work out is the second ionization energy, which is this one here, and I'm going to call this X. Now, there's multiple ways of doing this. I'm going to show you the way that I do it, but I think this is really good. So essentially, we're going to use the idea of Hess's law. If we start at the bottom at 0, we go all the way around, we're actually going to end up at 0. So if you go all the way around, we're going to end up with 0. So what you can do essentially is add up all the arrows and equate it to 0. And I'll show you what that means. So I'm going to add up all the upwards arrow. Why is there 1 electron affinity for chlorine? Shouldn't there be 2? Yes, there is. So that's why I put minus 364 times by 2. So here electron affinity of chlorine is minus 364. And then I times it by 2 here. Yeah? So if my downwards for my formation is minus 795, my upwards is going to be positive 795. Tick. I'm going to add 193. Cool. I'm going to add 590. I'm going to add X. I'm going to add 121 times 2, which is 242. Then I'm going to subtract, because this is going down, minus 728. That's just going down. I just did that real quick in my head. And then minus 2237 going down again. And using the definition of Hess's law, this must equal to 0. If we start at 0, we're going to go all the way around and still end up at 0. And then we just go ahead and rearrange for X. I think this method is really, really good. You can start from anywhere actually on point of the graph. It doesn't have to start at the bottom. I think starting at the bottom is nice. Follow the arrows method. That's why I call this method. I will take credit for making this method, but I'm sure it's already been made. And then we just essentially rearrange. Plus 242, minus 728. There would be a second electron affinity. 728 minus 2237, and we get X is X minus 1145 is equal to 0. Therefore, X is equal to 1145. That's our answer. Okay. Now, if you're ever worried about whether your answer is positive or negative, just look at the direction of the arrow. The direction of the arrow will tell you if it's positive or negative. Up is always positive. Down is always negative. Okay, just remember that. But the arrows can also be flipped around. Cool. That's calm. 1145. Light work. Let me give you guys another one. Okay. Next one. Boom. Have I got this? It says use the data in table 1 to calculate a value for the electron affinity of chlorine. There were stuff up here, and I know it says 3 marks. I crossed out. I kind of rubbed them out so you guys can have a bit of work on figuring out what the bits are within the bond Haber. So technically, it should be more than 3 marks, but it's all right. Okay, but let me know once you guys got a value, and then just put it in the chat. Okay. Well, secret, you found that helpful, yeah? Appreciate it. Do you have any predictions what will come up in your paper 1 chemistry? I think there's going to be redox titration. I think there's going to be a transition metals E equals HV. So this, you might remember this, you might not. If you haven't, then it's a very small part of the spec. I think this will pop up in the spec. I think group 7 will pop up. If there's a transition metal 6 marker, that would be beautiful. I think potentially it could come up as transition metal 6 marker, but I don't think it will. What do I think a transition metal 6 marker will be on? It could be on ion testing, which I think will be a really nice 6 marker, but I don't think they're going to be nice. I don't know about the 6 marker. It could be anything about that. Time of flight always comes up. Period 3 will come up. I think electrodes this year will be in. No, last year didn't. Nope. Last year came up about a catalysts. 2024 was catalysts. That was a really good 6 marker, and loads of people I know weren't able to access it because they didn't bother memorizing the equations. It was in a 6 marker transition metal. Yeah. But I'll tell you, the catalyst stuff I think will pop up potentially also catalysis equations. Potentially, maybe vanadium, but no, vanadium is, yeah, maybe vanadium, maybe. Yeah. Shapes and isomers for transition metals. Potentially, I'm thinking if it's a transition metal 6 marker, what's going to happen is it's going to give you a random molecule. It's going to tell you to make the equations. Catalyst is inorganic. That's why. It's inorganic. It's not organic. It's inorganic. Vanadium is contact process. Yes, and no. The one I'm talking about, you're talking about V2O5, which is vanadium. You're correct. What I'm talking about is when it's with zinc. So when it's used to essentially reduce zinc. Yeah. But I'll give you all the equations today, anyways. But if transition metals comes up, what's going to happen is they're going to give you a molecule. They're going to tell you the shape of the molecule. They're going to ask you the color of it, give the equation on how to make it, and then give you like another shape of another like octahedral structure, which will be a nicer one. But yeah, they'll probably be like copper, Cl4. Yeah, organic kinetics rates. Yeah, basically, yeah. Yes, it's live on YouTube right now, actually. So if you want to come to YouTube, come. There's a link tree in my bio. Just join that. Okay, let's start this. I'm gonna start with the equations. So we have what they have done is they have. Am I tripping? Am I tripping? Yeah, I'm tripping. They've just done atomization on the chlorine. I don't know why that took me so long. Sorry. They've kept the strontium the same. Is strontium? Yeah, it's strontium. And they've made the chlorine into the 2Cl gas. Okay, and then they've done the ionization energy for the strontium. And then there's probably going to be another strontium 2 plus up, so it's going to be Sr2 plus 2Cl gas plus 2 electrons there. Perfect. There are 2 possibles for equation 1, are there? Okay, we'll look at that. We've got first ionization energy. You got 2 possible equations. How have you got which 2 possible equations have you got? Because the reason why is because your ionization energy happens up here. So the only thing it can be is atomization of chlorine, no HM, unless you can prove me wrong. Anyways, first ionization of strontium, that's going to be 548. You could do first IE of you could do first ionization of that. No, I would argue no, because you have a 2Cl gas here, no? But I see what you mean. I see what you mean. You can, yeah. The reason is because they were actually given equations given to you on the top. Either way, your equations will still be the same. Like in terms of the final answer, your final answer will still be the same. Okay, it doesn't really matter the order, but they'll give you a Born-Haber cycle in a way such that the order it doesn't have two answers. But if it does, don't panic. Your final answer should still be the same if you do your maths correctly. Cool. Second ionization is 1060. Cool. For enthalpy of atomization of chlorine, remember the definition of atomization is when you make one atom. So 1 mole. So if we have Cl2, that's going to be 2Cl. So we're going to be timesing by 2. So if atomization is 1 to 1, so we're going to times by 2. So that's going to be 1 to 1 times by 2 here. Cool. Atomization of strontium, that's going to be 164 here. Cool. Formation of strontium chloride, that's going to be -828 down here. And then we also have -2112 down here. That's the formation. What we're trying to work out is the electron affinity of chlorine. It's not too bad of a question, and this would be, you can do 2x or -2x. I'm going to keep it as 2x because you'll get x to the negative number. And then we just follow the same way. We're going to start from 0 and we're going to add to 0. This is AQA. You can have Born-Haber cycles in OCR as well. Edexcel probably does Born-Haber cycles. I don't know much about Edexcel, I'm going to be honest, so sorry about that. But this is more AQA focused today's stream. But OCR 100% they're welcome. We're going to start from 0. We're going to end off at 0. So we're going to go up. So we have 828. We're going to go up again, which is 164. And we're just going to keep on doing it as we discussed before. I'm going to add up all the numbers, and then we're going to subtract. But I'm just going to add 2x because we'll get x as a negative number anyways. But if you do -2x, let's say you accidentally do -2x, which is fine. You can just know that it's a downwards arrow, so your final answer has to be negative anyways. And then we're going to do -2112 is equal to 0. And then we're going to rearrange this for x in our calculator. If we do the following, 828 plus 164 plus 242, I've just times it by 2 in my head, 548 plus 1060 minus 2112. So I get the following, 2x plus 730 is equal to 0. That means that 2x is equal to -730. That means that x is equal to 365. Why is it 2x? Is because we have 2 chlorines, right? They're going to 2 Cl minuses, and it says electron affinity of chlorine. So that's why it has to be 2x. I know I've put a -2x here. You can put minus or plus, it doesn't matter. Your final answer has to be negative. Why isn't it plus? Well, arrow going down is minus, arrow going up is positive. Yeah? Arrow going up is positive, arrow going down is negative. You got 463? Let me just double check. 828, 164, 2 times 121, 548, 1060. Can we double check if I've done something wrong? If I've done any calculation wrong? Maybe I've done some multiplication wrong. -365? We got -365, we got -463. Can we get another answer, please? And because I got -365 divided by 2. Okay, yeah, cool. Alright, cool. So -365. Amazing. Nice. Perfect. Any more questions on that? If not, let's move on to the next topic. Group 7. Alright, nice. Perfect. Okay. I don't have anything. Well, I do have some questions for Group 7, but before we go to Group 7 stuff, get writing, because this is going to be a lot of equations that you need to know. I'm going to do buffers towards the end. I'm going to get my notes up because I'm going to be real, bro. I've actually forgotten a lot of it off the top of my head, but I've always got my notes. Give me a second. Okay. Inorganic. Here we go. So there is not necessarily one type of equation. There's more than one equation that you can put down and still get the correct answer. You can still get the mark. However, these are the equations that I recommend you learn. Okay. 268. That's a good way of doing it. I like that. I like that a lot, BMZ. So first one for chlorine. This is what you need to know for chlorine. Okay. When chlorine goes ahead, or when your sodium chloride goes ahead and gets reacted in a sulfuric acid test tube. This is to do with your fumes and such, and I'll show you some questions after this. Okay, when sodium chloride reacts with sulfuric acid, it makes the following: it makes HCl and it makes NaHSO4. Okay, it's a 1-to-1 ratio. This is a nice equation that you can learn, and this makes white fumes. Okay, now your fumes are going to be your HCl bit here. These are hydrogen chloride bits. I'll tell you what the 268 bit means. But yeah, chlorine acts as a base. Does it act as a base? It acts. Don't say base, because your sulfuric acid here, its purpose is the oxidizing reagent. So you call this the reducing agent. Okay, don't call it a base. It's a chlorine that's acting as a reducing agent. Okay, and in this case, chlorine is the weakest reducing agent, and I'll show you why in a second. Now, when we go ahead and react bromine, bromine goes ahead and says, no, I'm a stronger reagent, I'm a stronger reducing agent, so I'm gonna, no, you don't need state symbols, you're fine without them. I'm gonna go ahead, yeah, you don't need them. It's good to know for one question I've seen, but I'll tell you them anyways. It's not redox because oxidation states are the same. Are they the same? But you can yeah, sure, yeah. But that's not what definition of redox is. You can still have an oxidizing reagent, and you can still have a reducing agent. Redox just means one thing gains electrons and one thing losing electrons. It's not redox, but you can still have an oxidizing reagent and a reducing agent. Reducing agent just means it's giving electrons, but it can still have the same charge at the end. Does that or oxidation number at the end. The purpose of your sulfuric acid is an oxidizing reagent. Agent. I don't know why I said reagent, oxidizing agent. Okay, that's the purpose of it. If it asks you, generally, by the way, if it ever asks you about sulfuric acid, put down sulfuric acid as a catalyst. Okay. However, in group 7, this is not the case. It's an oxidizing agent in group 7. Yeah. Okay. NABR. NABR or bromine. We're not really bothered about the Na that much. It's the bromine that's doing the work. Bromine is a stronger reducing agent, and it goes ahead and reacts with SO4 and still makes the same type of equation. NaHSO4. But there's another equation you need to know for this. This HBr goes ahead and reacts with more sulfuric acid and makes the following. It makes bromine gas, it makes SO2, and it makes 2H2O. Okay? This is a more stronger reducing agent, and you need to know these equations by heart. If you want to cram them, you can cram them. It's up to you, but you need to know these equations by heart. And finally, the strongest reducing agent. And, oh, sorry, this is not balanced. There should be a 2 in front of there. I would recommend that you learn it without balancing, and then you balance it in the middle of the exam. I would recommend you do that. So I'm going to put the numbers in front, but I would recommend you learn it without the numbers. Okay. Now, with iodine is also the exact same. You have the first two equations that are the exact same. So you have Hi plus NaHSO4, exactly the same. You have Hi plus H2SO4 makes I2 plus SO2 plus H2O, and obviously the numbers are the same here. Now, knowing what each bit does, so this part here, I'll also kind of label what's going on with this. Up here we have orange. Yeah, of course. So we have these two. Just these two equations you need to know. I would recommend you learn without the numbers. This is going to be your orange. there's going to be an orange liquid in there, but most of the time you're going to have orangey fumes. Okay, the first one you're going to have white fumes. The next one, you're going to have these for your iodine. Now your iodine is a black solid. That's the first thing we need to write down. Okay, black solid. And we also have two more equations that you need to know. And I recommend this is the way you learn it. We have Hi plus H2SO4, and write this down 2 more times. Okay, this is not for OCR, by the way, this is only for AQA. What we do is we keep I2 at the beginning and we keep H2O at the end. Still the same, right? I2 will also make a brown solution, yes. It will make a brown solution, yeah. Black solid or brown solution, either's fine. Okay, and in the middle, we'll put sulfur, and we also make H2S. Now, something to note, which may be, you're right, you're right. It is the HBr makes the orange fumes, the NaHSO4 makes the white fumes. That's the reason why you make the missing fumes. You can call it orange liquid or brown liquid, doesn't matter. Okay, for iodine is more brown / dark / black. Either's fine. Okay. This is good to know because H2S and SO2 are gases, and your sulfur is your solid. This is going to be a yellow solid, your sulfur, and your H2S is going to be your smelly gas. You need to know these equations by heart. Now, by the 248, to the 268 that BMZ was talking about, essentially it's the balancing numbers. You don't need to learn the balancing, but you need them for your final answers, otherwise you don't get the mark. So I recommend you learn the equations without the balancing and then balance them in the middle of the exam. So these are the numbers, I'll put them in blue, that you need to know. So, oops, this is going to be 2, 6, and 8 here. It's going to be 2, there's no coefficient there, it's going to be 3 and a 4, and a 2, 4, and a 4. Okay, if you remember that the middle ones will have no coefficient, you should be fine. I would recommend that you balance using the waters first. It might make it a bit more easier. Okay, these are going to be your equations that you need to learn. If you learn these 4 equations, you should be fine with the rest. Okay, and the purpose of this is the oxidizing agent. It's not a catalyst. It's not a catalyst. Okay, and iodine is your strongest reducing agent. Okay. Why do these equations happen? It's a good question. It's because you go ahead and take the salt. You take the salt and you go ahead and react it with sulfuric acid. Okay, or like when in reality you don't have one reaction happening. You don't have one reaction happening in a reaction. You have loads and loads of different reactions happening. So these reactions essentially happen at the same time. Okay, and because iodine is a stronger reducing agent, you essentially have more reactions happening in comparison to the chlorine. Fluorine doesn't do anything, I can't lie. Fluorine is just there for vibes. You'll never be asked about fluorine. If you ever are, just say it's the weakest reducing agent. Okay. Shit. Oh no. Oh no, I got inactivity on TikTok. Oh that's bad. That's bad. Oops, I don't know why that's happened. Okay, I'm back live on TikTok, but can't lie, chemistry gives so much time. I know. So that's why I recommend you learn it without the numbers. If you learn the numbers, then great. If you haven't, then whatever. Okay, there are some more equations you need to know in terms of group 7. Now, group 7, I will go over the iodine testing, the halide testing in a bit. But group 7, you have the following. You also need to know these. When you go ahead and react sodium hydroxide, these are just extra bits. You can learn them for your 1 markers. I think these will pop up probably. What type of questions could they ask about this? I have a couple of questions I will show you afterwards. I'll just give you the equations first and then we'll go over the questions in a bit. Okay, so cold sodium hydroxide and reacting with chlorine. These are just literally just equations. Cram this. Yeah, this is your bleach reaction. So sodium hydroxide plus chlorine makes NaClO plus NaCl plus chlorine. Okay, these equations you literally just cram. Okay, I can't lie, it's inorganic is that type of subject which you just cram. That's 1. Second, chlorine in cold water. This is going to be Cl2 plus water. It's a reversible reaction to make HCl and HClO. And this is used to kill microbes. This is for your pools. This is for your, to essentially like clean your pools. Where does the H go for your Na or HCl? Good question. That's a very good question. That's a very, very good question. Where does that go? It might be supposed to be a H. Shit, it might not be balanced. Yeah, might be H. Yeah. Sorry. That's not. Yeah, that's wrong. Sorry, that is wrong. H2O. H2O. That is correct. Yep. You're right. You're mad. Let me just double check that. That'll be H2O. Yeah. Yep. Absolutely right. No, you're right. You guys are right. H2O. Cool. 1 second. 1 second then. 1 second. That is very, very... Appreciate that, guys. Appreciate that. Cool. Alright. Last one that you need to know. Chlorine and water in sunlight. And this is going to be chlorine plus water makes HCl and oxygen. Okay. Obviously, some of the equations will not be balanced. Like this one's not balanced. Just balance it. This one's not balanced. Just balance it. But if you really want to know, there's going to be 2H. Going to be 2. No, that one's balanced actually. That one is balanced. This one's not balanced, but I'm probably just going to put a half here. And 2 here. That's balanced now. Yeah. Okay. So these 3 equations, they can just ask, and those are the equations you need to know for group 7. Okay. Sorry guys, in terms of TikTok, what topic is this? Please write in comments down how to sound. This is group 7. But yeah. Okay. For the guys on TikTok, just come onto YouTube. I don't know why. Sorry, I had the inactivity thing. So it just literally just turned off. Sorry about that. Cool. Lastly, in terms of the content, it's just iodine. It's just not iodine. Halide testing. Okay, I will give you the script for halide testing, and this is what we're gonna have. Yeah, this is AQA. Yes, but this part's even OCR. This halide testing bit. The first thing what we're gonna do is add nitric acid to our sample. So if you have a sample, okay, we're gonna add nitric acid. Why do we add nitric acid? To remove contaminant ions. Oh yeah, there's titanium as well. Okay, cool. Contaminant ions. I'll quickly go over that. I was gonna go over that in terms of group 2. That was more magnesium, but sure, I'll throw it in there to remove contaminant ions. Then what we're gonna do is you take your silver nitrate and you go ahead and react the sample with it. Now, if you ever ask you about ionic kind of equations, I'll show you how to make the ionic equation. Let's say we have a chlorine ion. Well, if you have silver nitrate plus your chlorine ion, this will just make silver chloride and a nitrate ion. But since we want a full ionic equation, everything that's aqueous gets separated out, and everything that's solid remains the same, and I'll show you what I mean by that. So this becomes Ag plus NO3 minus. We separate the aqueous ions out. The solid remains the same, and we keep this aqueous. We cancel out everything that's on the other side, so our final ionic equation will be Ag plus Cl minus makes AgCl, and obviously that's a solid. Okay, that's your final ionic equations, and that's how you make your ionic equations. If it was chloride, if it was bromide, anything. Okay, and in terms of the colors, this is the colors that you need to know. If it was chlorine, I'm going to write these all down. Chlorine is going to make a white precipitate. Bromine is going to make a cream precipitate, and iodine is going to make iodide yellow precipitate. Okay, cool. Next, let's say we need to differentiate between these ions. what you have is the further test called the ammonia test, and what you can have is the following, where you have dilute ammonia and you have concentrated ammonia. Okay, and what you'll find that it dissolves these precipitates, or some of these precipitates, and this is a little table that you can learn. Yep, so chlorine gets dissolved by, I'm going to put dissolve here. Chlorine gets dissolved by dilute ammonia, but it does not get dissolved by, bromine does not get dissolved, and iodine does not get dissolved. Chlorine gets dissolved in concentrated, and also bromine gets concentrated, dissolved in concentrated, but iodine does not. Okay, so that's the way you can differentiate between the different precipitates. It's a precipitate that specifically gets dissolved, not the chlorine, the bromine, and the iodine. It's a precipitate, the silver chloride precipitate that gets dissolved. Okay, and if it ever asks you about the equation for that, let's just use silver chloride and ammonia. I believe it is 2 ammonia off the top of my head. You can have AgNH3. I believe it's just NH3 even. It depends on the charge. I think they would probably tell you on the charge, but NH3 plus Cl minus. Just simple as that. All the different colors of the nitrogen oxides, you don't need to know that for AQA. If you needed to know for Edexcel, I don't know off the top of my head. I'm sorry, man. Okay. Cool. Let me make a new page. And we're in a good position right now. I like this. I'm going to show you the different questions where it can come up. So here, write an equation for the reaction of chlorine with cold water. Sorry guys. Well, cold water is what we just went over now. So that's going to be Cl2 plus H2O. Reversible reaction makes HCl and HClO. Now, why is this good? Is because it kills microbes. And why is it bad? Chlorine is toxic. So if too much is used, it's not good for us. Too much is used. Cool. Well, all the difficult chemical tests. Yeah, they can be difficult chemical tests. I'm dying, man. I'm dying. Alright. Okay. Yeah, I mean, there are difficult chemical tests. I'll go over a couple. I won't be going through. I mean, I should really, but you have the halide tests. If you did the normal, in this case, yeah, you would. I would recommend you try to put the reversible. You have the halide test. You have the group 2 stuff. The carboxylic stuff. I think that one's not too bad. I'm going to be focusing on really the chunky markers. If you're unsure about ion testing, just have a quick search on Google. That's going to be your best friend. Okay. Let's continue to look at some more questions. This one's good. Should I do this one? 1 second. Sodium chloride react with this. This one's good. This one's good. Alright. Write this down. Have a go. I'm gonna be back. I'm gonna go to the toilet real quick. I'm gonna take a quick piss. I'll be right back. Alright, I'm back, guys. I'm back. You guys on TikTok, tap the screen, man. Give me a couple taps. Okay. Alright, solid sodium chloride. We've got NaCl reacts with H2SO4. This one's a nice equation. NaHSO4 plus HCl. Simple. We did some redox titrations earlier on. I want to try to get to transition metals as quick as possible, to be honest. That's my main focus on acids and bases. Next, give an equation for sodium bromide when it reacts with this. And then give one other observation. This one's actually not too bad either. But it says, wait 1 second. Sodium dioxide that formed with sodium bromide reacts with... Oh, okay. So this one is actually slightly different. The reason why is because we know that when we react sodium bromide, normally we just make this. Right? Yeah, fair hectic. Yeah, 100%. I think it'll come up. I think a redox one will come up this year. But the difference is because we know that sodium bromide reacts with this, right? Kind of what we need to do is just add the equations together. So we know that sodium bromide plus H2SO4 makes NaHSO4 plus HBr, right? And then our second equation would be HBr plus H2SO4 makes SO2. Oh, sorry, I'll start with Br. Br2 plus SO2 plus water. And this should be balanced. If I balance this, it becomes 2, I believe. Yes. And then what we do is essentially combine the two equations together. And what happens is you'll have some sort of cancellation. Oh, let's just combine it together. We'll cancel the stuff afterwards. Sodium bromide plus 2 sulfuric acids plus 2 HBRs makes NaHSO4 plus HBr plus Br2 plus SO2 plus 2H2O. We're going to cancel out the HBRs, so we end up with HBr, 1 HBr on the left and no HBRs on the right, and that's going to be essentially our equation. Let me just check. How come you got 3? 1 second. 2 NaBr multiplied by 2 HBRs. How come you multiplied by 2? Why do I combine the equation? Essentially, it's because it's a sodium bromide reacts with sulfuric acid to make sulfur dioxide. We need to make an equation with sulfur dioxide. That's why. I'm just trying to read what Imad has said. And 2 HBr plus H2SO4. You know, I like that. I think that's probably a better answer than what I've written. I completely agree with that. I like that a lot. So you know what? I'm going to stick with what Imad said. So I'm going to times it by 2. This as well. So essentially what Imad has done, he's times his equation by 2, so he's able to cancel out the HBRs completely. So this becomes 2, this becomes 2, this becomes 2, this becomes 2. And what happens is these end up cancelling out completely. So we end up with 3 H2SO4s. But either way, you will actually end up with the same answer anyways. Sorry, the mark anyways, because you're trying to just show an answer that has SO2. It's still valid. Okay. This should be a 2, and that's fine. That's also 2. Yeah. 2 NaBr, 2 H2SO4. Yeah, that's fine. BMZ, that's fine. Na2SO4 is completely fine as well, by the way. As long as you have something that's chemically right, that's fine. There's not one right answer with these. Okay. The reason why I'm using the NaHSO4 is that's what I've been taught from right at the beginning, 2, 3. That's my foundations, and that's what I'm kind of like. That's what I'll teach everyone else. But Na2 is also fine. Na2SO4 works. That is a valid answer within the mark scheme. I've seen the group 7 mark scheme. I've studied them myself. I've studied the chemistry mark schemes. There's not one right answer with them. So as long as it's chemically right and you're doing what the equation is asking for, we made an equation, even the one that I gave you before, made SO2. That's still completely fine. Okay, so I really like the way that Imad has done this. So I'm actually going to stick with what he's done. Perfect. Cool. Observation. Well, we make orange fumes. What's the role of the sulfuric acid? Oxidizing agent. Amazing. This is AQA. But we're going to be looking at some more other stuff as well. Alright, we're going to move on. Are you allowed to do ionic equation? I'm going to say the reason why you can't in this is because your sodium bromide is solid, Victor. Ionic equations work when you're working with in terms of aqueous. I would advise you say orange fumes, don't say white. I would advise you say orange. I know white fumes, that you've been taught white fumes. I would advise you say orange. If you say orange and white, that's fine. If you said white completely, you get it wrong. Orange is very important because it's bromine. Okay, just how to differentiate between oxidizing and reducing agent. Just remember, this is just a remembering thing. Your sulfuric acid is your oxidizing agent. Okay, just remember that. Either it's your oxidizing agent, 95% of the time, H2SO4 is usually a catalyst. You've probably seen that in many exam questions. But in group 7, it's an oxidizing agent. But the definition of an oxidizing agent is that it gets reduced. Okay, so oxidizing agents get reduced, and using the definition of oil rig, they gain electrons. Yeah, 100%. If you look in the description of the YouTube, it's going to be in there, or yes, look at the description of the YouTube. It's there. Yeah, oil rig is your guy, man. Alright. Group 2, I'm also going to quickly go over. And then I might actually skip over period 3 just because I want to get into transition metals. Actually, no, I'm going to skip over period 3 for now. I'm going to do catalyst equations real quick. And then I'm going to do some transition metals. Because I really want to start that. Just looking at time as well. Okay. Group 2. Group 2 I think is very simple. So, what you need to essentially know about Group 2, this is the main thing even. What you guys, you want period 3. Period 3 is not harder, bro. Period 3 is just memorization, man. It's just, period 3 is literally memory. It's so small. Okay, I'll do period 3 after this. Fine. Let's do period 3 after this. If we got enough yeses. Okay. Don't really care about radium, to be honest. But for group 2, essentially, barium sulfate. Know that barium sulfate is insoluble. Okay? So if barium sulfate is insoluble, as you go up the table of your sulfates, they become soluble. Okay? Vice versa for your hydroxides. Your hydroxides will be insoluble on the top. Specifically, your most insoluble is going to be magnesium. You don't really care about beryllium, so I'm actually going to cross out beryllium as well. These are the 4 that you mostly look at. Okay, and then your barium hydroxide is going to be very soluble. Or I'm going to say not insoluble, but barely soluble. That's the actual term of it. BaOH2 soluble. Aisha, why do you combine them? For the second equation, do we not get the fumes? We do, but the reason it says when sodium bromide, I'm just going up real quick. When sodium bromide reacts, in the second equation, we don't use sodium bromide. We only use HBr. So we need to have an equation which has sodium bromide as a reactant. Essentially, that's why we have to combine them. Okay. Yeah. Okay, cool. That's mostly kind of thing. If you're testing for your sulfate ions, what do the brackets mean? These brackets is the ionic equation, or the molecular equation of magnesium hydroxide. Is because Mg has a 2+ charge and OH has a minus charge. If you cross kind of work out the molecular formula for this, you have 1 Mg's and 2 OH's. That's just what this means. Okay. Cool. Now, if you're testing for sulfates, so what we'll have for sulfate ions, what we'll do is we want to make our barium sulfate precipitates. So essentially, we'll put in maybe a magnesium sulfate. When magnesium sulfate is really, really soluble, right? And then oh, sorry. I take that back. Let me take that back. Sorry. We're gonna put in magnesium. Sorry, I don't know why I'm using magnesium. Sorry. Let me start again. We're gonna test for sulfate ions. Yeah, you can tell I'm dying here now, man. This 4 hours getting to me. testing with sulfate ions, and we're going to use barium chloride. Okay, the reason why we're using barium chloride, yeah, there we go. The reason why we're using barium chloride is because we're trying to make, or we're going to try to make barium sulfate if SO4 ions are present. If SO4 ions are present, then what happens is you just make barium sulfate, and then your chloride ions, whatever they are, they might just bind to something else. They will essentially just hop off wherever they want, bro. It doesn't really matter. And yeah, you guys are right. You should be using acidified. It doesn't really matter too fair in AQA. I know most of the time they're not too fussed about it. Most of the time it's going to be your barium chloride, but acidified is better. And that's it. If you make barium sulfate, sulfate ions are present. Cool. In lots of math schemes, I haven't really seen HCl. That I've seen it here and there. I guess it's better to put it. Acidified is always better, I think. But yeah, exactly the same thing for your hydroxide ions. We're going to be using magnesium chloride. Okay, and then what we're doing is we have our sample. Does the sample contain? I don't know why I put OH2. It's just OH minus. Is there a color change? No. What you'll find is a precipitate is made. Remember, barium sulfate is a precipitate. We're trying to make a precipitate. So magnesium chloride, we put in the sample, and we'll try to make magnesium hydroxide. Okay, if the sample does have hydroxide ions, amazing. Then your magnesium hydroxide is made, and you'll end up with a white, barely soluble precipitate. Your magnesium hydroxide does have a usage, by the way, and your barium sulfate also does. 1 second. Yeah. So your barium sulfate has a. Let's start with the magnesium hydroxide. This is just one markers. Magnesium hydroxide is good for stomach medicine, specifically laxatives. Okay. Or you can say anti-acids. Yeah. Barium sulfate is used for your X-rays and through ingestion. So you ingest the barium sulfate and it helps. So ingestion medicine for X-rays. Okay. Medicine. And then we also have calcium carbonate, which is used for neutralizing soil pH. And while I'm on calcium carbonate, I will actually tell you the equations for calcium carbonate, because there are a couple you need to know, and also for titanium and magnesium as well. Let me find those equations. Cool. Barium meal. Barium meal? I don't know. Cool. Why does solubility increase down the group for hydroxide? It's because barium. Why does solubility increase down the group? It's because magnesium hydroxide is the most insoluble. That's why. This swap. That's why. Okay. Okay, there's a couple of equations you need to know for calcium. Yeah, for sulfur dioxide flue gas. Yep. So these are your flue gas equations. So these are the two you need to know. Calcium oxide plus sulfur dioxide makes calcium calcium sulfate. Sulfate? Yeah, sure. Calcium carbonate plus sulfur dioxide plus water makes calcium sulfate and carbon dioxide. Okay, these are two equations you might need to know. There's also an equation from year 1. I'm just going to throw it in. It's not really related to group 2, but it's catalytic converters. Some people know it, some people don't. I think it's just a nice one to know. It's just you learn it in AS and everyone just forgets about it. Carbon monoxide and nitrogen oxide makes carbon dioxide and nitrogen gas. Okay, I'm just going to throw that in there because I think it's just good to know. Okay, but it's nothing to do with group 2, to be honest, so it's just there. There's also an equation for your titanium extraction. Okay, these are equations just I want you to just cram as much as you can, and then if it doesn't come up in paper 1, just cram before your paper 3. They won't come up in paper 2 because it's just inorganic. I think this one's a nice one. You can actually probably figure it out in the exam as well, because it'll tell you to use titanium 4 But titanium chloride, it'll be titanium 4 chloride, by the way. I should probably put this chloride, titanium IV. Yes, history, yes. You don't really need to know the context about it that much though. Titanium chloride plus magnesium makes titanium, and what we left with magnesium chloride. Then we just go ahead and balance the equation. We need 2 of these, so we need 2 of these, and that's it. Cool. That is group 2 more or less done in terms of the equations. That's more or less it for group 2. Testing, that's about it. Alright, let's go ahead and move on. Let's do period 3. Period 3. Give me a second. One second, guys. Let's get my period 3 notes. Okay, got them. Alright, so period 3. This is period 3. We don't care about chlorine that much, and we don't care about argon that much. Okay. So these are essentially what you need to know about period 3. Every single one of these atoms or elements can react with oxygen to go ahead and let me go up real quick. This will be recorded. If you're interested, just go on my YouTube. It will be recorded completely afterwards. These are all the stuff you need to know for group 2. Cool. Okay, period 3. These are all the atoms that are relevant, and they can all react with oxygen in some way. Okay, these are kind of basic. This is the basic stuff for period 3. So I'm going to quickly brief over these. Sodium plus oxygen makes sodium oxide. These are not balanced equations, but you can balance them afterwards. I'm not going to balance them. Magnesium and oxygen makes magnesium oxide. Aluminium and oxygen makes aluminium oxide. This one's an interesting one because this one has something called amphoteric properties. And does anyone know what amphoteric means? If you want to put in the chat, what does amphoteric mean? And I'm going to continue on writing the rest of them. Silicon plus oxygen makes silicon oxide. Phosphorus plus oxygen makes good. Yes, history. Amazing. They act. Thank you guys. They act as an acid or a base. Phosphorus and oxygen. This one you need to know. Okay. Phosphorus oxide is P4O10. Remember this. I'm actually going to balance this one. Remember what phosphorus oxide is. Sulfur plus oxygen can make SO2, but it can also make SO3. And the reason why it can make SO3, there's some conditions with this. It's when it has a high temperature and a catalyst. Okay, but you don't really see that. You really just work with more SO3 stuff. But yeah, good. These are essentially the oxygen stuff. You don't necessarily need to memorize these like with hearts. You can probably figure them out on the spot. But probably the more interesting one is probably this. Okay. Cool. That's good. First history, man. I'm gonna write that down. V2O5 with 450 degrees. You need to know the. I'm actually going to do the catalyst equations. Yeah, it is SO3. I was literally about to say that it is a contact process. I will go over the contact process after the period 3 stuff. Actually, no, let's do it now. Oh no, let's do it now. Let me get the equations up for the contact process real quick. So the contact process essentially is your catalyst equations, and these ones you need to know by heart. Okay, so the overall equation, this is the overall equation for contact process, where SO2 reacts with oxygen to make SO3 via a catalyst, specifically V2O5, and you can see that's essentially SO2 here reacting with this. That's essentially what's kind of going on. But this is the actual equations for your contact process. So what you're going to have is following: SO2 plus V2O5. This is your vanadium. Okay, this goes ahead and makes SO3 and V2O4, and then simply your V2O4 reacts with this oxygen here from the beginning, and then that makes V2O5 again. That is the definition of a catalyst. It reacts with whatever. Well, there's technically two definitions of a catalyst. One, it reduces your activation energy, and two, it's regenerated via at the end of the reaction. They're more or less the same thing though, but this is going to be your equations for the contact process. Okay, cool. Let's continue on with the period 3 stuff. Let me just check on TikTok if there's any questions. Cool. Let's continue on. Now, your atoms can also go ahead and react with water. These are more of the two that are going to be relevant. So sodium reacts with water, and this makes sodium hydroxide. You need to know this, and also hydrogen. I'm not going to balance the equations. I know it's not balanced, but this is the basis you need to know. Magnesium also goes ahead and reacts with water, and this one will make magnesium hydroxide. Now, magnesium hydroxide, I didn't talk about this in the group 2 bit, but there's something you need to know about magnesium hydroxide, is that its pH is around like 10/11. The reason is because it could really be a strong base, but because it's really insoluble, the ions just cannot get released, so it's considered like a weakish base. It's not as weak as like ammonia or anything, but it's considered a weak base. Okay. Good. Just about to say that. I'm actually going to put liquid here. When magnesium goes ahead and reacts with steam, the state symbols are very important here. It makes magnesium oxide and H2, and there's an observation for this. It's a violent reaction, and it's a bright white flame. Okay. Cool. Very good. Now we're going to start to look at some of the more equations. Yep, amazing. White solid, yep. I'll put that in there actually, white solid. Cool. Perfect. Alright. Next, these ones are probably also self-explanatory. Sodium plus water makes sodium oxide and water makes your sodium hydroxide. Don't know why I forgot the name of that. Magnesium oxides plus water. You can start to see the pattern here. It's very, very repetitive in my opinion, and you can probably start to figure this out. Now, with the other ones, this is where it gets a bit more different. For the guys confident with your period 3 stuff, you probably already know this, but we're going to be using this bit here for the next part. So we need to think about, well, phosphorus oxide and water. Well, if these made a base, well, phosphorus is going to make an acid. Why does it make an acid? It's because you can't really have a phosphate base. It's just more acidic. So you make H3PO4. This is phosphoric acid. Okay. You can also do the same thing with SO2 and SO3, but the difference is a different type of sulfuric acids. So SO2 will make H2SO3, and SO3 makes H2SO4. With Si2 doesn't, but your aluminium oxide does. And this is where the amphoteric stuff comes in. Your aluminium oxide is amphoteric, so it can react in 2 ways. This one, I'd say you learn. The second one, actually no, both you should learn actually. This is when your aluminium oxide acts as a base when it reacts with, let's use sulfuric acid. Okay, and it's not limited to sulfuric acid. It can be hydrochloric acid. It could be any type of acid. You need to be able to make the equations on the spot. Okay, so aluminium oxide, when you have sulfuric acid, this makes, well, salt plus base plus acid makes salt and water. So you can make aluminium sulfate. So aluminium has a charge of 3, SO4 has a charge of 2, or 2 minus. Cross multiply, Al2, SO4, 3. Okay, simple. And what else do you make? You make water. Okay. Is it balanced? No, it's not balanced, but you should balance it. I'll balance this one for you. This is going to make 3 waters, and that's it. This is your base reaction when it acts as a base. But you can also have aluminium oxide act as an acid. So when you do that, you're going to be reacting with this. You react with sodium hydroxide, and you go ahead and react with water. And it makes the following. It makes this stupid looking molecule, but if you've been revising your transition metals, you should be familiar with this. Does anyone know what the colour of this molecule is if you've been revising your transition metals? Is it 3H2SO4? It probably is 3H2SO4. It is. Yeah, Adam, you're right, yeah. Nope. It's not white. Not white. Nope. Not white. Not blue. Thank you, Hectic. It is colourless. Colourless. Well done. The guys who said colourless, you're correct. So this is actually from your transition metals. When you have excess, I know this is not balanced. I know it's not balanced at all. It should have probably 4 here. I know it's not balanced. But I know, is it balanced? You should probably have a 2 here, I'd say. But pretend it's balanced. Pretend it's balanced. You can balance this. This is AQA, yes, but it's AQA, yeah. But since you have excess hydroxide ions, you make AlOH4 minus, which is a colorless. Is it 3OH2? H2O. Thank you. The Al ion solutions, they are actually white. This is the exception. Most of them are actually white. You only have the original solution, which is colorless, and this ion, which is colorless. Okay, so this is excess OH ions. Okay, do not say clear. Clear is wrong. Make sure you say colorless. You can have clear. Clear just means it's see-through. So you can have an orange. You can have orange solution that's clear. Essentially, that's see-through. That's wrong. Do not say clear. Say colorless. Okay. Cool. So this you need to know. Is it balanced? No, it's not. Is it balanced? Let me check. 2 sodiums, 3 oxygens, 3, 4, 5, 6, 7, 8 oxygens. That's balanced. Yeah. All right, cool. Appreciate the guys who told me about the balancing stuff. Appreciate it. Cool. Because I don't like balancing. I would just recommend you learn it without numbers and you balance it in the middle of the exam. That's how I would recommend it. Okay. Cool. The rest of the stuff, I think, is pretty nice. So you go ahead and if you go ahead, I should remember. 3 hours of Kevin's crazy, man. If you go ahead and react to acidic oxides with your bases, they actually kind of act as acids almost. So it's like an acid-base reaction. So this is gonna make sodium phosphate. So sodium is Na plus, and phosphate is 3 minus, and you're gonna make Na3PO4 and water. Okay. Again, it's not balanced, but yeah. Okay. Acts in the same way with SO2. Acts in the same with SO3. I'll show you the ones of it anyways. You don't have to memorize these, but I will show you which ones you have to memorize after I've given you all the equations. These are the last set of equations anyways, actually. But you can figure these out on the spot. Sodium hydroxide, SO2, you know in the beginning, SO2 makes H2SO3. So this is going to make an SO3 ion. So Na1, SO3 is going to be a 2 minus. So this is going to be a Na2SO3 plus H2O. Again, make sure you balance. And similarly, do the same thing. This one make an Na2SO4 plus H2O. Okay, how did I know? By the way, SO3 is a 2 minus. Reason being, this is a H2 here, so therefore SO3 must have a 2 minus charge. Okay, I will go back up. I'll go back up in a second. Last one. This one is the one you need to memorize because it's the only time where silicon is used. It doesn't get used anywhere else really in terms of equations. Silicon oxide plus NaOH makes the following. It makes Na2SiO3. SiO3 has a 2 minus charge. Learn this. So if you know that SiO2 is just on its own, that's this oxide. If you add an oxygen to it, it must have a 2 minus charge because oxygen is 2 minus. You just add an oxygen. So if SiO3 is 2 minus, Na is plus, combine them together, it makes Na2SiO3, sodium silicon oxide, and then plus water. Okay, I will highlight which ones you need to know. Let's highlight it in green. This one, I'd say you need to know. These two, you need to know. These ones you can figure out on the spot. These ones you can figure out on the spot. This one you need to know. I'd say these ones that you can probably figure them out. And this contact process you also need to know. Okay, and then we'll go over the characteristics of the stuff now. Yeah, it's not balanced. You do need to balance. I know it's not balanced, but I've just given you the base structure. Balance it in the middle of the exam. I don't have the. Yeah, I haven't got it written down in terms of balanced. So yeah, I should probably balance it in my notes, but it's not. Oh well. Okay, cool. For the guys on TikTok, come to YouTube. Why not? From YouTube. Appreciate the rose, man. Yes, this is period 3. Yes. Okay, last bit of period 3 is just the characteristics of each of the molecules. Okay, so the way the melting points work of your molecules, essentially it looks like a graph like this. Okay, something like that. It's not fully accurate, but it will be something like this. Okay, and these are to do with your oxides. Give me a second. P4O10 and SO2/SO3. Now your sodium oxide, you can see it's right at the beginning. And actually this probably shouldn't be that low, to be fair. It should be a bit higher. Something like so. The reason why it's so low at the beginning is because we'll just talk about the characteristics and then we'll talk about the temperature in a second. Sodium oxide is going to be an ionic bonding, and actually I'm going to add in magnesium hydroxide as well. Sorry, magnesium oxide. You guys are going to have to bear with, bro. I've been streaming for like 3 hours straight. So if I make mistakes, please bear with. Okay. Sodium oxide and magnesium oxide, we have ionic bonding. And we'll just talk about how there's strong electrostatic forces between them, oppositely charged ions, and so on. Okay, and it requires lots of energy to overcome. Okay, this is your basic script for your ionic bonding stuff. Why is it that magnesium oxide has a stronger, has a higher melting point? Why is it that it has a higher melting point than sodium oxide? Anyone know? Thank you, Anita. It does have a 2+ charge. So it has a higher charge density. Mg has a higher charge density. And you can actually be asked about this. And this is actually, I'm going to give you a full maximum answer. Good. So it has a higher charge density. Therefore, it is smaller. It is a smaller ion. If it's a smaller ion, thank you, H. It requires more energy. And you can see it's more exothermic. Okay, essentially the same thing. More energy to overcome, or more exothermic. Okay, cool. Yeah, exactly. Yeah, amazing. I'm gonna add that. In. Stronger attraction to O2 minus. Perfect. Bang on. Cool. Next. Aluminium oxide. Now, aluminium oxide is a slightly different one. Again, it's because of its amphoteric character. Now, aluminium oxide, in terms of its melting point, remember these are not just one molecule. You have loads and loads of different molecules between these, right? Aluminium is a 3+ ion. Okay, because of its high charge density, what happens is it distorts its own electron cloud. And if it distorts its electron cloud, then what happens is it gains some covalent character. Now, this is kind of to do with your bond-Haber cycle stuff almost. Or if I ever ask you about bond enthalpy stuff, covalent character essentially means with ions, let's use sodium, the more spherical an ion is, the more perfect it is. That's like the term of it. So it's called a perfect spherical model. And that's what your Born-Haber cycle is based off of. I know this is period 3, but this is what your Born-Haber cycle is based off of, called the perfect spherical model. But what happens is when you have aluminium 3+ and it interacts with oxygen, well, yeah, they have oppositely charged ions. I'm going to pull up the periodic table real quick. Let's go back up to here. You can see that oxygen and aluminium, they're not that far apart, whereas in comparison, sodium and chlorine, they're miles apart. That's why they have a stronger electrostatic force. Whereas aluminium and oxygen, because they're closer together, they don't have a high level of difference in the electronegativities. Okay, so that essentially means it's very, very kind of close to your essentially being a covalent bond, but it's not a covalent bond. It essentially distorts your dipoles. So you might have an aluminium that's like a 3+ and O2, 2-, and obviously you have different O's, like so. Al 3+. Now these are not just spherical ions where these are like attracted by like ionic bonding. No, they're almost like a covalent bond, but they're not a covalent bond, and that's what's called a covalent character. Okay, you don't just have ionic bond, covalent bond, blah blah blah. It's a whole spectrum. Okay, it's a spectrum. So you have perfect ionic bonding, and then you have full covalent bonding. And then the more the electronegativity is, the more the electronegativity difference, the more the ionic bonding towards you get. And that's where you get dipole-dipole bonds, intermolecular forces, and such. Okay? Does that make sense? So this is essentially mark scheme answer. Just put down it distorts the electron cloud, so it gains covalent character. And that means that it still requires a lot of energy to overcome, but not as much as magnesium oxide, because magnesium oxide is quite high up there. We already went over group 7. If you want to watch the live back afterwards, young, it will be in there. Okay. A lot of energy to overcome. Okay, cool. Sorry, not lots. I'm tripping. I'm trying. Sorry guys, it requires less energy than magnesium oxide. It requires less energy to overcome. Okay, cool. Alright, next what we have is our silicon oxide. Well, silicon oxide is your macromolecular stuff. Macromolecular, or your giant covalent structures. Okay, there are many strong covalent bonds. Many strong covalent bonds, and it requires lots of energy to overcome. Energy to overcome. Now the other molecules, the molecules that we've got left, P4O10, phosphorus oxide, SO2, SO3. These are simple molecular. These are very small molecules, and they only have van der Waals forces or London forces if you're doing OCR. And between, make sure you say between molecules, by the way. This is a key bit. Van der Waals forces between molecules, which can be overcome easily. Okay, why is it that phosphorus has more melting point than SO2? It's because it's just got more electrons, therefore it has more van der Waals forces. Okay, that's just the difference between them. Cool. Alright, let's move on to transition metals. Something I've been wanting to do for a while. How do you know how a molecule has permanent dipole or induced dipole? Induced dipole is called the van der Waals force. Okay, a permanent dipole is, for example, HCl. So HCl isn't sorry, it's not ionic, it's covalent, because is it covalent? It's covalent, or is it ionic? I'm tripping, bro. I'm actually tripping. I would say try write it out, but you should be okay, to be honest. I would recommend you write it out fully, MK. Let me just try to think off the top of my head of another, because chlorine. Let's just use chlorine. Chlorine and chlorine, they have the same electronegativity. So this is called at the moment these have van der Waals forces, and why they get induced is depends on essentially if there's another chlorine and chlorine. This will cause an induced dipole, which is called your van der Waals forces or your London forces. If you have, let's use HCl. I don't know. I can't remember if HCl is ionic or not. I don't know why I'm just thinking it's not ionic. Someone correct me. Is HCl ionic or not, bro? I'm a chemistry teacher and I'm being stupid here. But essentially, chlorine is really delta net. Yeah, it's not ionic. Cl is it? It's covalent. Oh, it's covalent. It's covalent. It's covalent, right? I'm not tripping, am I? Yeah, it's covalent. Yeah. Yeah. Okay, cool. Cl, yeah. Cl is delta minus. H is delta plus. Okay. Now, if it's delta minus, your dipole would kind of look like this. You'll have a higher electron density around the chlorine than the H, and that's called your permanent dipole. Okay, yeah, I wasn't tripping, yeah. I wasn't tripping. Yeah, ionic is metal, non-metal. Yeah, cool. Yeah, I mean, silly guys, my bad. Okay, let's do transition metals. Let me make a new page. I'm going to try to go as fast as possible in terms of transition metals. And you're going to need to know every single one of these. Boom. You guys ready? Why is it telling me some brother sent TikTok universe? What's TikTok universe? Guys, what's the TikTok universe, bro? Okay, anyways, where we at? Cool. So we've got iron 2, we've got iron 3, we've got what else have we got? We've got copper 2. But let me put copper 2 first, actually. And we've also got aluminium 3+. Okay. So iron 2, these are the things you need to know. Make yourself a table just like this. Okay. These are going to be the ions. This is AQA. For OCR, I'm gonna actually, if you're OCR, 1 second. If you're OCR, I'm gonna put a screenshot on your screen. Just take a screenshot of that. But either way, stay around for the equation bit because you're going to need to know how to make the equations. Okay. This is for OCR. If it decides to copy. 1 second. Copy image. Wait, what the heck? Why is it not doing that? Copy, paste. Bruh. 1 second. Give me a moment. Technical difficulties. Okay. If you're an OCR, this is what you need to know. Take a screenshot of this, but stay around for the equations bit because this is what we need to know. Okay, you can make a table for this if you want. You need to know this word by word for the names. Okay, this is directly from the OCR specification website. Okay, but we're going to be doing AQA stuff. Alright, let's get started. Give me one more moment actually. 1 second. Just getting my aqueous ions notes up. Because I have the equation stuff in there. Is it this one? It is this one. No, it's not this one. It's this one. Yes, okay, I got it. Alright. Iron 2. What you're going to write down on the top is we have our aqueous ions. Now you need to know your shapes for these. And all of these will generally be octahedral. So iron 2, pretty simple. Fe, you have 6 waters. And you're going to put big brackets around it. If it's a 2, iron 2 is going to be a 2+. Pretty simple, right? You need to know the colors for this. Iron 2 is green solution. Okay? All your aqueous ions will be green. All your aqueous ions will be solution, I mean. Copper 2, pretty simple as well. Blue solution. I've lost my stream. Like this, for the differences in terms of AQA and OCR, I know in OCR you might say pale green for the solution. Just bear with because it's AQA focus, right? But yeah, okay. Copper, Cu, H2O6, pretty explanatory, self-explanatory. It's pretty simple, okay? And they're all going to be the same. Copper is going to be blue solution. Cool. Iron 3, Fe, H2O6, again following the same pattern. Try to recognize the patterns here. This is brown solution. Aluminium, iron 3, it depends. Some say purple, some say purple. I know in some specifications you see purple. Brown is fine. If you do AQA, brown is fine. you'll get full marks. If you learn purple, purple should be okay, but in mark schemes it says brown more. Okay, you will still get the mark with purple though. Okay, I recommend you just put down brown. You get the full mark. Alright, aluminium, AlH2O6. This is going to be a colourless solution. If you've learnt it as purple, purple's fine for iron 3, by the way. Alright, next. Okay, next, we're going to add drop-wise OH minuses. And I'm going to slow down here, actually. And this is where the equation's coming. So I'm going to use iron 2 as an example. Okay. Iron 2, when we have our aqueous ions, and this part you gotta watch carefully, right? When we have iron 2 aqueous ion and we react it with sodium hydroxide, I recommend you use OH ions, especially when you talk about transition metal equations. Make sure you talk about in ionic form. Okay, we're going to use OH minus ions. Now, how many are you going to use? Just use the same amount as your charge. We're going to use 2 OH minus ions. If it's brown, they're all brown. Okay, you'll see that all of your iron 2s are green, except all of your iron 2s are green. All your copper blues are blue. All your iron 3s are brown. Like, that's why I'm saying stick with brown. Okay, I know there's a couple of exceptions here and there in terms of your colours, but they're more or less the same. That's why I'm teaching you these colours, so it remains the same. Okay, in terms of your equation though, when you go ahead and react your hydroxide, I'm actually going to go ahead and draw this in display, and I'm going to show you what's happening, because this is not a substitution. I'm not show you what's going on. So what happens is your OH comes along and says, okay, I'm a base. Okay, I'm gonna rob one of your H's from each of your waters. Okay, so you have H's here, and this OH acts as a nucleophile, essentially, attacks one of the H's and takes it. If it takes one of the H's from two of the waters, if you have two OH's, if it takes one of the H's, what do these become? What do these become? Waters, correct. So they become waters. And what we're left with on our original molecule is we're left with 4 waters and we're left with 2 OH's. Now the charge of OH's, you know, is minus, and that's where our minus charge also develops from. So we have our original molecule here. This will make the following. Fe, we have 4 waters, so H2O4. We have 2 OH's. We know the original charge of Fe is 2 plus. We know that this should be OH2. We know the charges of OH, 2 of them is 2 minus. This cancels out to have no charge. 1 second. Cool. Yeah, this cancels out to have no charge. And then what are we left with? We're left with 2 waters, and there we go. It looks like a ligand substitution, but it's not a substitution. It's not a substitution. Okay. It is a robbery. That's what it is, bro. It's a robbery, man. But yes, it's neutral in charge, and the color of this is going to be a green precipitate. Okay, and this is what's going to happen up here. Using this logic, can you guys figure out what the formula will be for copper 2, iron 3, and aluminium 3? We'll worry about the colors in a second. Use the same logic to work out copper 2, iron 3, and aluminium 3, and write the equations as well down. You don't have to put square brackets because it doesn't have a charge. And this is green precipitate, by the way. Perfect junk. It is. And I will write the equations down as well. So if you guys need to know the equations, but I would rather you guys figure out the equations. Okay, use that logic to figure out the equations. Okay, so this second one is a 2 plus charge. So we're just gonna again, copper is a 2 plus charge. So we're just gonna attack 2 OH minuses, and it will be the same. Okay, in terms of the equation, is exactly the same. Your CU's just get swapped from the F's. Okay, perfect for the guys that put that in the chat. You're absolutely right. That's how that would look like. I'll write down the copper ones anyways. I would recommend you don't memorize these, by the way. I know I'm writing them down, but I would avoid memorizing these. Figure them out on the spot. For your Fe3 plus and your aluminium 3 plus, I'll just write the Fe3 plus 1 because it's exactly the same. You're going to use 3 OH minuses. Okay, you're going to produce Fe 3 waters, and you're going to produce 3 OHs, and 3 waters come off. Will they all go to neutral charges? Just produce 2 water, some produce 3 water? Yes. Don't think of it as producing, do they all produce neutral charge? Don't think of it like that. Think of it as, what is my overall charge just from the reaction? So I've got 6 waters originally, right? And then suddenly what happens is I've got 3 OHs, 3 FEs. I know my charge is Fe for 3 plus. I know my charge is 3 plus for Fe. I know my charge is -1 times by 3, which I'm left with -3. What's my overall charge? 0. Okay. Don't memorize it. Figure it out. Okay. And it will also be the same for your aluminium. So these are going to be your equations: H2O3, OH3. Try to spot patterns as you do this. Okay. I'll tell you the colors. This is going to be blue precipitate. This is going to be brown precipitate. And this is going to be white precipitate. Okay, when do you know if it's an acid-base reaction or a sub? Most of them are going to be acid-base. There is only one place where it's two places where it's a sub. Actually, 2 places. And I'll show you where that is. Okay, next. We're going to look at excess OHs. So excess OH, you'll find that some of them actually have no change. So here we have no further change and it remains the same. Here we have no further change and remains the same. No further change and remains the same. But here we have a difference. Yes, NH3 is a sub, but when it's excess. So this is where we were looking at the period 3 stuff. Your aluminium hydroxide, well, even this molecule here, you should probably start from this, reacts with excess OH. So what happens is Al, H2O, 3, OH3, goes ahead and reacts with more hydroxide ions, and essentially is still a basic reaction, and what you end up with Al, H2O2, OH4. Either this molecule is completely acceptable, or if you've learnt it as this is also acceptable. They're both the same thing. And they're colorless. Okay. In terms of reaction, in terms of equations, I recommend you write this down as your equation. And actually, there should be a H2O on. It should be a plus H2O here. Sorry, plus H2O. Why is it a minus charge? By the way, this is a 3 plus, and this is a 4 minus. That is your overall 4 minus charge. Okay, and it's a colorless. So that's going to be your molecule. On this bottom part, I'm going to write AlOH 4 minus. They're both acceptable. Okay. Do that again. It's just going to be this molecule here. This acts as a base. I'll show you what happens in terms of this. OH2, OH2, OH2. Sorry, H2O. Okay, and then you got 3 OHs on the bottom. It can be anywhere really, doesn't really matter. You have an OH that comes here. It attacks one of the waters, being like, okay, I'm gonna finesse you. Okay, gone. What do you have left? You have 4 hydroxides left. The OH minus and the H plus react to make a water, and then they make this part here. How can aluminium form a transition metal complex when it's not even a transition metal? Good question, to be fair. Good question. All of your aqueous ions, the definition of an aqueous ion is to have waters all the way around it. Okay, so all of these bonds, all of these things are called ligands. Okay, so they are dative covalent bonds. They are giving electrons towards the aluminium. They are dative covalent bonds. So I get that. You know what? Fair enough. That's a very good argument. I never even thought about that, to be honest. I don't know why I didn't think about that. But yeah, yes, V, yes, they're both the same. They both are acceptable. Okay. But remember, these are all dative covalent bonds, and I should probably look at my PowerPoint because I wrote some stuff about EDTA and stuff like that. We'll go over that in a second. All right, cool. Drop-wise, NH3. Very, very similar. In terms of your molecule that you make, you actually make the same thing. you actually make the same molecules. I want you guys to make me the equation for copper 2 with dropwise NH3. I want the full equation. I want the full equation for copper 2 with dropwise NH3. Using the same logic that we had here with acid-base reaction. Is it acid-base? More of a hydrolysis reaction. Tell me the full equation of it. Using copper 2 with dropwise NH3. Okay. Or if you're willing to give me the side products, that also works. Guys, tap the screen if you're on TikTok, please. Tell Birds to come. And I'm also streaming on YouTube. So if you wanna come. Yo, drop me a couple of roses, guys. Give me a couple of roses. Give me some roses, bro. See you NH36. It is not Lila. Good. Because it only got one extra electron of the D subshell, it formed the 3+ charge of the ion. Potentially, I'd say yeah, I agree with that. Yes, Abdullah, yes. Yes, Farah, yes. Good. Good, Ibs. Good. So we make NH4 plus as our side product, and I'll show you how that works with this. So we have Cu. I'm going to do H2O. I see we are doing it correctly in terms of the chemical formula. Oh, that looks horrendous. That looks so bad. Yeah, let me just fix it. One sec. O H2 O H2 H2. Okay, there we go. Okay, now this is a copper 2+ ion. It should really have brackets around it to be fair, but that's alright. I'm going to split 2 of my waters up. Boom, boom. Okay, I have 2 NH3s. These act as nucleophiles. They attack my waters and they rob one of the H's. What happens is they take off one of the H's, be like, yeah, calm, and then they attach to each one of those, and what you have is your final equation, H2O6 2 plus 2 NH3s makes Cu it's exactly the same actually as before, OH2, and this time we make a different side product, 2 NH4 pluses. Okay, in this case you don't have a charge on your molecule, but it's exactly the same. Okay, so it's exactly the same for these. You're going to make Fe H2O4 OH2, the same product, but it's important to know about the equations. Green precipitate, I'm just going to copy this across actually, like so. Cool. Any questions on that? Sorry, electrophile. Is it electrophile? No, it's nucleophile. It's electrophile. No, nucleophile. Because donating electrons, accepting electrons. Is it accepting electrons? It's robbing it, bro. It's not doing either, man. It's not doing either. It's just robbing. It's robbing the H, fam. It's a base even. Accepting proton, it acts as a base. It acts as a base. You know, with the aluminium with precipitate rediscover to form colorless. Is that because it's amphoteric? Yes. Essentially, yes. Would it be? Yeah, it'd be a base. When the copper ion resolved, yes, it was. Yes, it would. History, yes. So this part, we're gonna make. So these part remain the same when we do dropwise NH3, but the next part when we have excess NH3, this happens. No change for the top. No change for iron 3. No change for aluminium 3. This time, what we're going to do, you can either do it from the beginning. I would recommend you do it from the beginning, actually. 1 second. Give me a sec. Okay, yeah. You can do it from the beginning if you want, or you can do it from here. Either way, it doesn't really matter. I would recommend you do it from the beginning. So if you had excess, so Cu H2O6, now this is where you're going to have essentially a ligand substitution. Your ligand substitution occurs when you have an excess of ammonia. Specifically, you have to use 4. I couldn't really figure out a way of remembering it really nicely. You just have to remember it like that. It's 4. It's not 2. It's 4. It's 4 ammonias, Ethan. And then you make Cu H2O 2 NH 3 4s. It doesn't replace all the water, just 4 of them. Okay, and it's still going to be a 2 plus because your ammonia doesn't have a charge, and you have 4 waters as your replacement. Okay, that's how you would do it in terms of that. But if you were forced to, for example, if you were forced to make an equation from here, which in some cases you might be, I'm just going to try to think off the top of my head. Is there a way? 1 second. There is. Essentially, it's still a ligand substitution. Still a ligand substitution. What you're going to do is still use 4 NH3s, and you're going to take off 2 waters, and you're going to take off 2 OHs. So you end up with the same molecule. Actually, I'm just going to copy this down. Same molecule, but this time your 2 waters come off and 2 OHs come off. Okay, and you can see the charges actually do balance out. Charges on the left, nothing. 2 plus and 2 minus is also just do that. In this case, it doesn't act as a base. In this case, it actually acts as a ligand substitution. Okay, it acts as a ligand substitution in this case. Okay, when it's excess Lila, when it's excess ammonia, then this happens. So this is for excess. And yes, absolutely correct. This is going to be deep blue solution. Absolutely correct. It's a deep blue solution. Cobalt got removed. It got removed. It used to be there, but cobalt got removed. Okay. I mean, you can learn it if you really want to be safe. I feel like you guys don't be peek. Don't be peek in chat. Imogen's my guy. Don't be peek. Will I do buffers? Will I do buffers? That's a good question. I could do it for another hour, to be fair. Might spray as well. This is AQA, but OCR, in terms of OCR, I'll show you the screenshot again. Okay, this is going to be the molecule for this, H2O2 and H4. NH3 2 plus. Okay, and lastly, we're going to react this with carbonates. So it can be sodium carbonate, any sort of carbonate. And this is where it's going to get a bit more tricky. First two I think are pretty nice. Iron 2 and copper 2. So iron 2, I'm actually going to move this down. 1 second. With iron 2, it's pretty simple. You have Fe H2O6 2 plus, and you have CO3 2 minus. Try to stick with your ions. Okay, this is a 2 plus. So what happens is you just make Fe CO3. Pretty simple. Fe is a 2 plus, CO3 is a 2 minus. They just bond together, and you get 6 waters as your replacement. Pretty simple. Okay, what is the color of this? Anyone know the color? Or guess what the color is. You can kind of, yeah, good. It's just green. It's green. It's not blue-green. It's not blue. You'll get marked down for that. This is green. The next one is blue-green. It's not blue-green, guys. The next one is blue-green. So for copper, H2O6 2 plus CO3 2 minus makes CuCO3 plus 6H2O. Blue-green is for copper carbonate. Okay, don't say blue-green for iron. There we go. Okay, iron 3 and aluminium 3, they will make essentially the same product here, and you guys are going to need the reasoning for this. So essentially, iron 3 plus and aluminium 3 plus, they have high charge density, and this is a mark scheme answer. Get this down. Okay, they have a high charge density. So if it has a high charge density, essentially what happens is they weaken the H2O bonds in their complex. So for example here, they weaken the H2O bonds. So if they weaken the H2O bonds, what happens is H pluses get released more readily. Therefore, it's more acidic. Okay, so it's because of the high charge density. And what happens is if they act as acids, and if you're reacting with sodium carbonate, well, acid and base, they make carbon dioxide and water. So that's what we can do in terms of the equations, and that's what we're going to figure out right now. Okay, so aluminium. Let's do with aluminium. Iron 3 is exactly the same, really. Aluminium 3 plus plus carbonate ions. Yeah, you can say polarizing. I would recommend you say high charge density, because with high charge density, with strong polarizing power, with that we also have to say they're a smaller ion. Okay, the thing with high charge density, it automatically covers a point that it's a small ion. Okay, so if you say polarizing power, alongside that you have to say they're a small ion. With high charge density, it means they have strong polarizing power and they're small. Okay, so that's why I've said high charge density. It just gets that whole point alongside it. Yeah, this is transition metals, Grace. Yes, player. Yeah. They weaken. What do you mean they create a dilution? They don't create a dilution. They weaken the waters in the complex. Okay, so we go ahead and then what we're going to make, we're going to make the same complex here. So we're going to make this exact same complex, AlH2O3O3, OH3. We're going to make carbon dioxide, and we're also going to make water. Now honestly, this equation is the most irritating to balance out. So I'm actually going to tell you the numbers and the way I kind of remember this. Okay. Yeah, I've actually forgot it. I forgot it. Let me look at my notes real quick. I believe it's 3 and 2. It's going to be 2 on the big ones and 3 on the small ones. Give me a second. I'm going to tell you what I mean by that. Yeah, I'm right, yeah. So we have 2 on the big complexes and then 3 on the small ones. Okay, and the way you can learn this, that looks a bit weird, 1 second, H2O6. And the way you can kind of, I guess remember this is, if you've got a 3 plus charge, you'll probably make 3 waters. Because look, there's 3 here. So this must be 3, so this is 3, so that's 2, and that's 2. You can think of it like that. That's the best way I could really remember. Like, you can balance it in the middle of the exam, but to be honest, this balancing is really long. I'm gonna be honest. Okay, so I recommend you actually learn the numbers here. Swap the charges. Did I mess up the charges anywhere? Oh yeah, you could do that. Yeah, that's a good way of BMZ. Yeah, exactly the same for Fe. Fe3 plus, exactly the same. Okay, and that's all of your transition, all your equations for transition metals. Done. Now he was selling a method. He was selling a method to memorize it. I like that. Okay, this makes a white precipitate, and this makes also a brown precipitate. Okay, boom. Studies for your tutors. If you look on my link tree, it should be there. It's better to understand it, but if you memorize it, sure. Colors you just gotta memorize, but you can see here they're exactly the same. The first row is full green, second row is all blue, third row is all brown, last row is all basically white, except 2. Oh yeah, carbon dioxide is your effervescence. Yeah, that's gonna be your observation. So carbon dioxide will be your effervescence. Effervescence. Okay, cool. I'm just trying to think, is there anything else off the top of my head? These 2, oops, not that one. This one and this one are your 2 exceptions. Okay, so everything else follows the same pattern. The rest, they're gonna follow that sort of rule. Isomerism, yeah, I was literally about to go over that in terms of cis-trans. I've got on the list. Give me a sec. Let me just see what list have I got. Okay, so we have 2 molecules, technically 3 you need to know. So you've got 2 molecules here. So you have ethane diode ions, and they look like this. Yeah, of course. It's going to be recorded afterwards anyways, but here you go. And what I'm actually going to do, I'm going to attach this. If you want this a bit more neater, what I can do is give you a screenshot of, if I find this, wait a second. I believe it is this. Give me a second. Let me attach it on screen right now. And again, I have sent this in my Discord. Here we go. And I will also go over this bit here in a second. This is essentially what I've basically based it off, but again, this doesn't have your equations. This used to be in the spec, but they removed it from the specification website. I have it, but yeah, this is the cobalt one. You see the copper ones you actually do, I would recommend you learn. So these ones you already know. I would recommend you learn the CuCl4, but I'll go over that each one. Yeah, this is for AQA. But OCR one is slightly different. The cobalt ones I would avoid you guys learning. You can learn it if you really want to for safety, but they won't tell you to like put down a cobalt one. It's just been removed from the spec. That's why. But yeah, okay. Anyways, let's go back to the transition metal stuff. So this is the ethane diode ion, and this is going to be C2O42-. You need to know how this looks like. And when you have any sort of complex, whether it's cobalt, copper, or whatever, the way it binds, that is horrendous. 1 second. One moment. 1, 2, 3, 4, 5, 6. There we go. So it's going to bind in an octahedral way, and where it's going to bind is from its the negative charge with the lone pair on the oxygens. Okay, so you have 1, 2, and you can draw this in structural formula if you want. Sorry, skeletal formula if you want, and you can make it look like this. Okay, and when you attach all of these molecules like so, what you end up with, and you might be familiar with this, is you'll have your cis-trans, or in this case you won't have a cis-trans, you'll have an optical isomerism. So this is one way, and the optical isomerism is going to be for it'll be flipped across. So yeah, your IBM's 100%. Okay, so essentially you can see that this is bound on the left, going towards the left, and this one will be going towards the right, meaning like this. Looks more or less the same, but it's considered a different molecule because of the way that this is a 3D structure. Okay, but yeah, exactly. So I was literally about to mention that. So this is one of your molecules, and you will be expected to be able to draw this in both of these ways. So these are your two isomers, and in terms of the charge, this will have a well, copper has a 2+ charge. This will be a 2-, 2-, 2-. So this will be a 4- overall. Okay, so I'll just put brackets around this. It'll be a 4- overall. Okay. This is a bidentate ligand, yes. You can also have another bidentate ligand. So if I draw copper again, your other bidentate ligand is ethane 1,2-amine. No, 1,2-diamine, 1,2-diaminoethane. 1,2-diaminoethane. And that essentially looks like, or you might see as EN, by the way. Never ever write EN. Never write that. But you might see as EN. But essentially, and what I mean by that is like CuEN instead of having the whole thing. But what that looks like essentially is CC, NH2, H2N, and then you have H2 and H2 here. How does it have a 4- charge? It's because copper has a 2+, and each of these C2O4s is 2-. That's why. So each of these oxygens will have a charge, a 2- charge. So 2-, 2-, 2-, that's 6- plus 2+ makes a 4-. Unless I'm tripping. Okay, so this is your 1,2-diaminoethane, and it works exactly in the same way. I'm not going to do the other isotope, the optical isomerism. Sorry, I meant isomer, not isotope, isomer. 1, 2, 3, 4, 5, 6. We're going to be binding them to the nitrogens. In this case, that's where your dative covalent bond will come from. Your 1,2-diaminoethane does not have any charge. Okay, and you can just kind of draw it like this, which is nice. Okay, I recommend you draw it in skeletal. It just makes it easy to draw. Okay, and then your other isomer will just essentially be flipped, kind of like that. I know it looks a bit weird, but kind of like that. Okay. Yeah, 100%. This is OCI will 100%. This will be useful for that. What else we can have is cis-trans. So I'm gonna go over the yeah. So if you ever have H2O 4Cl2, anything like this, essentially what this means that if you draw this out as an octahedral structure, you can have Cl and H2Os anywhere basically. It depends on where it says. But when you are binding them and it tells you, okay, we need it in a cis-trans, our transition metal reactions, you did the same. Yes, it is. That's all aqueous ion stuff. Yes, I see it. when we're doing cis-trans stuff. So in this case, this is actually going to be a cis structure. When you have something that's right next to each other, so especially in this case, we're talking about CLs, this is going to be a cis structure. If you're going to do trans, and by the way, there's not one right answer with this, but if you're going to do trans are going to be 180 degrees across. Okay, so this would have to be directly across, which would be down here. Okay, easy one I'd say is just put one on the top and one on the bottom. I think that's probably the easiest way. So Cl, OH2, H2O. That's also a trans. Okay. But cis is going to be right next to it. Okay, cis is right next to, trans is like on the opposite side. Okay. Cool. Let me see what else have we got. EDTA and properties of transition metal properties are pretty simple. I'm going to quickly go over this. Technically, I should have gone over this at the beginning. Yes, this is adjacent. Yes, right next to. Trans is all the way on the opposite side. I did have a 3D. Let me check if I still got it. I think I lost it. Yeah, I had like a 3D thing. I showed it to someone. Anyways, properties of transition metals. I should have gone over this at the beginning, but let me just throw it in there. They're good catalysts. What else are they? They have variable oxidation states. You might just see some like 1 markers, and they make colored aqueous ions. And also, yes, they have incomplete D subshells. I'm actually going to try to find a question in terms of this. 1 second. E equals HB questions. Because I feel like this will come up this year. 1 second. Don't the 3D drawing for those? Don't we have to do the 3D drawing stuff for those complex ions and ligands? Yeah, you do. Give me a second, guys. I have a feeling that you will need to know E equals HV. Let me see 1 second. I did it with one of my students this morning. Let me just get that up real quick. Essentially what I'm talking about is this. If you're familiar with this, great. If you're not, I'm going to quickly go over this. Let me find where it is. Here, I found it. It's very, very small topic. It's a very, very small topic. And essentially, it's part of your transition metals, and it's to do with how your how the D subshell works. And I'll go over that script actually before I do this question. So the way that you see color, of an aqueous ion is basically, yes, Planck's constant. The way you see it essentially is that a transition metal has an incomplete D subshell. And essentially what that means is because if you remember back in year 1, you might have, whether you skipped it or not, you have your electron spins, right? Let's say an electron has a 3d7 subshell. That's going to be 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6 electrons, and 7 electrons. And you can see that these are free. If I had a full subshell, 8, 9, 10, you can see they're not free anymore. We need them to be free. And if they're free, what happens is the electrons can become promoted or excited to the next energy level. And if they're promoted to the next energy level, you need to learn this formula, by the way, you need to learn this. I'll come to this. It's like context of this basically, but this is also, they can ask you in terms of a question as well, so I would recommend you learn this. Electrons can become promoted to the next energy level, and what happens is if they absorb specific wavelengths of light. Now if they ever ask you, and I've seen this in terms of I don't know where I've seen it, but I have seen it in terms of a specific complex. So if they absorb specific wavelengths of light, let's say Cu H2O6, right? Well, you know that copper aqueous ion is blue. They will absorb all the lights except blue, so they will reflect blue wavelengths of light. So you generally have to talk in terms of the context of the question. Therefore, we see blue. Okay, boom. That is an exam question style mark scheme. I don't have the exam question, unfortunately, I just don't. But I recommend you learn this. Okay. But what this essentially has in terms of context of is essentially this. It's to do with your wavelengths, and this is such a small part of the spec. And honestly, there's not many questions on it. And this is from past paper, actually. If you want to know, this is from 2022 paper 1, AQA. But let's have a look at this. It's pretty simple. You always end up with, they always give you the Planck's constant. Do you need to know the complementary colors? What do you mean complementary colors? No, they'll give you a molecule, and you need to know the color for that. So, for example, copper. You know what copper is. Copper is blue. There's essentially the same equation. This represents frequency. Technically, it's not a V, it's a Greek letter, and the formula for frequency is the speed of light over wavelength. Okay, so essentially, if you don't have the frequency but they give you the speed of light, or you might not even have the speed of light, they might give you just a wavelength, which is in meters, which is supposed to be in meters actually, but if it's in centimeters, make sure you convert it. Yeah, history, yeah. So just say the wavelength is reflected, but depends on if they give you a molecule, just talk in terms of the context of the question. Okay, so if it's copper, then say blue. If it's iron 2, then say green. Do you get me? But they won't give you molecules that you haven't seen before. And this is supposed to be wavelength. In this case, we can just use this equation, and it's pretty nice. This is a pretty nice question. You do need to know the formula, yes. So this is going to be, if you use this formula, energy is equal to Planck's constant times by frequency. We know energy is equal to 3.98. So we have 3.98 times 10 to the minus 19 is equal to Planck's constant 6.63 times 10 to the minus 34 times by our frequency. What's our frequency? Units is already given to you here in terms of seconds, but you can kind of work it out because you know this is in joules. This is joules per second. This has to be second to the minus 1, so you can kind of work it out there. But yeah, speed of light is going to be meters per second, and it is 3 times 10 to the 8 meters per second. Okay, and does anyone know what the frequency would be, or shall I work it out? You guys, if you're on TikTok, you don't want to come to YouTube, just tap the screen. Yes, this is AQA chemistry. It's a very small part of the spec. Very small part of the spec is going to be transition metals. I'm going to say, Amelia, I'm going to say yes to that. But chances are they might actually give it to you in the question. But it's such a small part of the spec that you'll be given the Planck's constant all the time. Did anyone work out the frequency? Yeah, it's a very small part of the chemistry spec for AQA. This is from 2022, paper 1, but there's not many questions on it. I'm gonna be real, man. There's very few questions on this. No one wants to give me an answer, bro. Oh, thank you, Sarah. 6 times 10 to the 14. Cool. That thing is quite big, actually. Actually, no, that makes sense. No, yeah, that's calm. Cool. 6 times 10 to the 14 per second. But yeah, I wouldn't be surprised if it came up this year. I actually would not be surprised because they haven't included it. Okay, last thing, chlorine in terms of your molecules. Did it come up last year? For what? AQA? Did it? I actually don't remember. Anyways, if you have chlorines for your full molecules, so if I have, for example, copper not hydroxide, if I have a copper molecule, it's a 2+ aqueous ion, and I react it with chlorine, only chlorine, and this is excess, what happens is this makes copper chloride. And make sure you put your ions correctly. This is going to be a 2+, that's a 4-. It'll make a 2- overall. Good, exactly. So what happens is, make sure you balance your equations as well. You make a tetrahedral structure. Why do you make a tetrahedral structure? It's because your chlorine ions are too large. They're larger than your water molecules. And what happens is they take up more space, So that means the maximum you can fit is 4. And yes, the color of this, and I would say you do need to know the color of this. It is yellow. Okay. I think the paper will be harder this year, Sean. Okay, I think that's more or less transition metals in a nutshell. I'm not going to go over hemoglobin or this EDTA, I guess. Let me quickly go over EDTA. I know I went over multi-ligand, bidentate ligands. Let me quickly go over EDTA. You need to know that EDTA has 6 coordinate bonds and is also 4- charge. Okay, so if you have, for example, Cu EDTA at any point, you're going to have a 2+ charge, you're going to have a 4-, and what happens is you're going to have 2- overall. Okay, cool. Let me just check my PowerPoint. Oh, this is perfect. This is perfect. This is perfect. Let's quickly go over this. Platinum, PD, and I. They're not really exceptions. I'm gonna be real, man. Like platinum, they're acting the same way. Like you have cisplatin. You have cisplatin, which is platinum, NH3, NH3, Cl, and Cl. Make sure these are in the right orientation. Yeah, I think so. MK. Yeah, I might do another 20-30 minutes for acids and bases, but yeah, I will try my best. Yeah, I'll do another 20 minutes. We'll finish at 7:30. This is your cisplatin. If you have transplatin, your things will swap. And this is a square planar. Okay, at 90 degrees. Okay, but anyways, let's try this question. I want you guys to give me the equation, and then we'll move on to acids and bases, and we'll finish off there. We'll do about 30 minutes of that. Okay, appreciate you guys for coming. You're doing really, really good. For the guys who've been here from the start, well done, man. It's yeah. Yes, it's for cancer treatment. Hell no, bro, I'm not doing it tomorrow, man. That's 4 hours today, bro. I'm not doing it tomorrow. Yep, so we have Al H2O3 OH3. What else have we got? We got observation. What's observation? We're gonna have effervescence, and then your equations for shape for 4 ligands. Yeah, they are tetrahedral BMD. They're not square planars. For CuCl4, this is a tetrahedral. Okay, for your cisplatin, they're gonna be square planars. Appreciate Ethan, man. I appreciate it, bro. Yes, this is AQA. Yo, I appreciate the rose, man. I appreciate the roses and the donuts and that. My guy Maka Paka. Nah, this is literally all you, man. This is all you. It's gonna be on my YouTube, Beth. If you go to my bio, it's gonna be linked. There's a link tree, and if you click Chemistry Live, you'll find my YouTube. Or just click the YouTube button. Yeah, smash it tomorrow. Seriously, man. Not tomorrow, Tuesday. Yo, let's up the grade boundaries, man. Yo, you guys are gonna up the grade boundaries. I'll be real. Alright, for the equation as well, Al H2O 3 OH3 is your product. I'm tripping. Al H2O 6 3 plus CO3 2 makes that product, makes H2O, makes carbon dioxide. We're gonna have a big 2, big 2, big 3, 3, and 3. Okay. Boom. Yeah, you should. I would recommend you should. It's better. Amazing, Abdullah. Perfect, man. Perfect. I would recommend you do ionic equations. It's just an easier thing. You don't have to worry about the sodium or anything. This should be a 3+, by the way. Alright, I'm going to take a quick 5-minute break, and then I will come back and we will start acids and bases. Okay, let me take a quick 5-minute break. I'm going to go pray real quick and we will start acids and bases, and try to do the buffer stuff as much as we can. I'm not going to do pH curves that much because it won't really come up. If it comes up, it'll be a nice topic. I'll brief over it, but it's something more for paper 3 than paper 1 that I'm more concerned about. But yeah, 5 minutes, back at 7:15. Okay, if you want to start a question, actually, I will actually put this question on screen. Let me put it's a nice question actually. Yeah, I'll put a question on screen. It's not a bad question, to be honest. Actually, you know what? Screw that. Let me leave that. One sec. I'm gonna put a buffer question on screen, bro. Boom. Alright. I'll be back, guys. Hi guys, I'm back. Alright. Sorry, man, I'm back, man. Okay, let's do this. Okay, first thing I think a good thing to do is to actually just write down the equation of itself. So what we have is propanoic acid and I'm assuming it's going to be sodium hydroxide really. But to be fair, let me just have a read of the question. No, we don't need to write the equation. We're just going to use our Ka formula. So our Ka formula is going to be H plus A minus all over HA. Cool. And we are trying to work out how much of the sodium propanoate we're going to be using. Okay. You guys got far? Oh, you guys can't see me. Oh, my bad. My bad. There we go. Nice. Come on, Will. Come on. Okay. Next, we just substitute the numbers in. We got 1.35. Oops. 1.35 times 10 to the minus 5. In fact, I'm not even going to do that yet. I'm not going to do that. I don't like really substituting the numbers in straight away. I'm going to rearrange in terms of the stuff that we got. We're getting 5.1, 5.2. I'm going to try to go through this quite quickly. And I'm going to rearrange for H plus. No, I'm not. I'm going to rearrange for A minus, because that's our salt. And that's going to be A minus. I know my Ka is the same thing as 1.35 times 10 to the minus 5. I know my HA concentration is going to be 0.25. I know my acid concentration, well, my acid concentration is 4.5, well, pH is 4.5. So that means that that's going to be 10 to the minus 4.5. I'm just going to put that here. If I stick this into the calculator, 1.35 times 10 to the minus 3 times by 0.25 divided by 10 to the minus 4.5. That's going to be 10.67. I get. I might have done something wrong here, but I'm just going to double check. It's supposed to be 10 to the minus 5, sorry. Yeah, it just didn't feel right to me. That's supposed to be 10 to the minus 5. Oops. 0.1067, that looks better. 0.1067. Cool. And then what we have is, that's our concentration, N equals CV. Do we have moles? No, we have concentration, we have volume, which is going to be 500 centimeters cubed. So I'm going to times this by 0.5. So 0.1067, which is my concentration, times by 0.5, which is my volume. That gives me my moles. Times by 0.5, and then that gives me 0.0533. Now, if I put that into my formula for mass equals mR, well, anyone know the mR for sodium propanoate? Just to save some time. I'm going to rearrange for, oopsie joules. My bad. There we go. Sorry, guys. 96, cool, 96.1, calm. Times by 96, 5.12, or is it 96.1? 5.128, yeah, cool. So that means that times by 96.1, that gives you 5.13 grams. Beautiful. Very nice. It's not a bad question, to be fair. I feel like you guys are pretty good in your buffer stuff. I don't think that is too much of an issue. I think, how do I know the value is given for HA and not H plus? It's because H plus is separate. H plus is to do with your pH, Farah. HA is to do with the acid concentration, which is this. I know that you know that it's 96. If it's 96, then fair. There will be some rounding stuff. If it's 96, still a very similar answer, 5.1228. Fair. Yeah, that's fine. It depends on if you round it. There might be some rounding errors. 5.12 to 5.13, that should be fine. Okay. Next question. I have a couple more questions on buffers. I'm going to put them on, or A minus. I'm going to put them on screen. I made these questions myself actually. I'm going to cross out more or less, yeah. I'm going to cross out this one and this first one. Yeah, of course. Is that okay, Emma? Yeah, there you go. Alright. Try these two questions. I'm going to give you guys like 2-3 minutes on each. I know it's not a lot. Kind of just looking at time. Or even, let's cross this one out. This is one more question. I want to do this one and then I want to look at one more. In terms of the adding the acid to a base, adding to acid to a pH curve. No, not a pH curve. Adding acid to a buffer solution. There we go. I've got 3 questions on that which I really want to focus on, because I think that's probably the hardest bits. Well, not even the hardest bits. That's like a very small bit of the spec. I think a lot of people are pretty confident on buffers. If you're not, then I'll try. I guess I'm gonna try to give myself until 7:45. Because we were supposed to finish at 7, but I know we didn't go through everything. Can I zoom? Sure, but come on YouTube, man. It's a bit more clear on YouTube. Okay. Alright. Start off by writing your equation. What you're gonna have is some excess stuff. I don't have the answer to these questions at all. What I'm gonna do is, if you really want, I can rub these out and you can have them as practice. But I don't have answers. I wrote these questions myself. So yeah, they're like based off actual questions. I've just changed the numbers and kind of the what's it called? The compounds. But everything's recorded on YouTube. So if you're on YouTube, if you're on TikTok, come to YouTube, and you can see a bit more clearer. Let me check TikTok real quick. Okay, and then I'll get started on the question in 1 minute. Start by making the question, by the way. The equation. And then that will help you out. Okay. I'm going to start by writing down the equation. So it says okay, this is the other type. Oh, okay, then fine. Let's do this type of equation then. Fine. Okay, these type of questions, they come up here and there, but they're a good 5 marks. In this type of a question, you're actually not going to be using an equation at all. In fact, you're going to be using a table. And I would recommend that for this type of question, you do this. You write down HA for your acid, and you write down A minus for your salt. Okay, and what you're going to do is this. You're going to make yourself a table, and you're going to put down initial moles. And because we're going to be working in moles, you'll see why. And also final moles. Okay. Now, whenever you have a weak acid, what happens is this gets dissociated into 2 things. This gets dissociated into H+, and it gets dissociated into A-. And actually, we'll look at some more questions here, just because they're actually similar. I thought it was a different type of buffer question, but it's just whatever. Okay. At the moment, at the beginning, we have 0.02 moles of potassium ethanoate. How do you know not to use an equation? It's because of this phrase here. 3 centimeters cubed of blah 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 is added to this buffer solution. That's why. That's why, Ali. Okay. If it says that phrase, you're going to be using the table. So you've already got a buffer solution. Essentially, what you're doing is you're adding sodium hydroxide, or you're adding acid to check, okay, what's the pH change going to be. My initial moles in my ethanoic acid, I'm going to put this into my calculator. It's going to be 0.26 times by 0.05. That gives me 0.013 moles. And just because I've made these questions, the pH values might be a bit dodgy, the final pH values. But generally, in your real exam, you should get around something from 4 to like 5.5-ish, maybe 5.8 max. Around there, that's going to be your range. Maybe even like 3.8. I'll write this down. Around like 3.8 to like 5.8 is going to be your buffer range. If you get any other values like outside this range, just think you've you might have gone somewhere wrong. So I would just double check your answer, but generally that's going to be your range. It's good to have an idea of like your ranges. Like your strong acids are like pH 0, pH 1. Your strong bases are like 14, 13. So just take note of that. I think it's a good idea to have like it's a good thing to have an idea of where the pHs are. Anyways, now when you think about how is our equilibrium of our weak acid affected when we add sodium hydroxide? If we add an acid, where is your equilibrium going to shift? Yes, this is for AQA, but to be fair, for OCR, I can't like this specific part. For OCR, I haven't really seen questions ever come up. If we add the acid, or an acid, good Arpan, it shifts to the left. If we add an acid, we shift to the left because we've added H plus ions. So equilibrium says, no, I don't want more H plus ions. I'm going to try decrease it to shift to the left. Therefore, with that logic, if we add a base, which is sodium hydroxide in this case, if we add a base, our equilibrium shifts to the right. Does that make sense? So if our equilibrium shifts to the right, that means we make more A minuses and less HA. Where did the 0.013 come from? I just multiplied these two together. Concentration times volume to work out the moles of ethanoic acid. Okay, you can put HA, you can put ethanoic acid, doesn't really matter. This specific question is more for AQA. How do we know it's a basic buffer or an acidic buffer? Most of your buffers will be acidic, to be honest. You don't really have weak base buffers. But to be honest, the elements will tell you really. Okay, if it's ethanoic acid, you know it's an acidic buffer. If it's something else, it's a basic buffer, but it's mostly acidic buffers. Okay, but does that make sense? If we add a base, equilibrium shifts to the right. If we add an acid, equilibrium shifts to the left. That's something you need to know, or you can figure out like we just did. So if we add a base, we know that more A minus is going to be made. But by how much? How much? So that's where this part is also very, very handy. 3 centimeters cubed of 1.4 moles per decimeter cubed of sodium hydroxide is used. Well, I'm just going to quickly work that out, how many moles that is on the calculator. 3 divided by 1,000, convert that to decimeters, that's 0.003, times by 1.4, that gives me 4.2 times 10 to the minus 3 moles. So I'm adding 4.2 times 10 to the minus 3, and I'm subtracting from the acid side. Then, what we're going to do is just add to the moles, because we're working in terms of moles right now. 4.2 times 10 to the minus 3. This gives us 0.0242. And the other one, you should end up with, since we're subtracting, 0.013 subtract 4.2 times 10 to the minus 3. 8.8 times 10 to the minus 3 you should end up with. If I've gone wrong anywhere, please let me know. Then we're going to use our Ka value, our Ka equation, and essentially it's the same thing. Ka equals H plus A minus over HA. And what you'll find that is you don't actually need to even worry about the volume, but you can use it. The volumes will actually cancel out. So what you can do is, especially with these type of equations, you can just substitute the moles in. So I'm going to do Ka, I'm going to rearrange for H plus actually. Ka times by HA divided by A minus gives me H plus. So what you have is Ka, which is 1.84 times 10 to the minus 5, times by my HA. You can just use your moles. Don't actually have to worry about your volume here, or your concentration here, since your concentration actually cancels out. I'll show you. I'll do divided by V, divided by my acid, my salt, which is 0.0242 divided by V, and you can see this just cancels out, so we don't actually need to even worry about the volume. Is equal to my H plus, and whatever this answer is, we will just log minus. Yes, Apan, yeah. And then in the equation, in the formula, in the calculator, we end up with times 10 to the minus 3 over 0.0242. Oops, I should supposed to be in the denominator. 0.0242 minus log the answer, 5.17. Does that make sense? Yes, history, yeah, exactly. Because they're on the same solution, it doesn't matter. Okay, but if you have three terms, for example, H plus, A minus, and HA, if you ever in that situation where you putting in H plus, then just be careful, because sometimes if you have two volumes on the top and you have one volume on the bottom, they don't really cancel out. Just be careful. Where did I get 4.2 times 10 to the minus 3? I times 3 centimeters cubed, well, in decimeters, times by 1.4 moles. So that's the moles of my sodium hydroxide. What do you mean? If they didn't specify what they want the limits in? What do you mean the limits in? I'm not sure what you mean by the limits. Okay, using that, I want you guys to try this question here. Okay. Try this question. Tell me what pH you guys get, and let me know. Oh, significant figures. Oh, always two. Always two decimal places of pH. Always two. Okay. Alright, try this question. Let me know how it goes, and then we'll go over one last thing. Two more things. Yeah. Just looking at my thing. Okay, yeah, we'll go with this one. Okay, yeah, that's cool. Let me know what pH you guys get. Just put it into the chat. Use the exact same method. Make the table. Decide what you're adding. Decide if it's your acid or your A minus that's increasing. And guys, appreciate you guys coming, man. Honestly, I don't get paid for any of this, so honestly, it's for you guys. Smash your A levels. I believe that honestly, everyone can do well in terms of A levels. You just have to have the right teaching. Hopefully, my teaching's alright. If it's not alright, then tell me as well. But yeah, if you're year 12 and you want tuition, definitely just drop me a message. Yeah. Appreciate it, Farah. Thank you, man. Thank you. Yeah, in physics. Yeah, honestly, I wish I did physics. I'm a be real, bro. I mean, I'm doing economics now, right? But honestly, I wish I did do physics. I'm honestly really interested in astro. There's like, you know what? I wouldn't mind becoming an astronaut, bro. Like, imagine, man's on the moon. Maybe in the future, man. Who knows? I'm gonna be in the moon, man. I'll be in Mars. I'll shout you from there. I'll do a chemistry lesson from Mars. No, it's calm, man. It's calm, bro. Chem is calm, bro. When's physics 2? Is it tomorrow? I know psychology is tomorrow. When's physics 2? I'm gonna start this question as well, actually. Damn, it's tomorrow. Yeesh. Alright, let me make the table for this as well. HA, A minus, initial moles, final moles. And you can put change as well. You can make a little slight change if you want. You got 4.24. Alright, we got an answer already. Nice. Double check with me with Imran if he is correct or wrong. Let me move more to the right. Give me a sec. Oh, we got another 4.24 in the TikTok chat. Arpan. Oh, what just happened there? Sorry. Cool. It's looking good. It's looking good so far. All right. We're gonna have the initial moles of potassium ethanol at 0.07 times these two. This should give you no idea what that gives you. We got another 4.24. Good. Just gonna calculate the initial moles. We have 0.2 times by 0.04. That gives you 8 times 10 to the minus 3. Here. Cool. Alright, we're going to do our dissociation. So acid dissociation goes to H plus and A minus. If we add hydrochloric acid, where does the equilibrium shift to? The equilibrium will shift to the left. Why? It's because you have more H pluses on the right. So you're going to have more of this, and we're going to have less of our A minuses. So we need to check how much are we actually adding. We have 30 centimeters cubed of 1.7. Good, Arpan. So we have 0.03 times by 1.7. That gives us 0.051. So we're going to minus 0.051 from the A minus. We're going to add to here. And what does that give us? I have no idea. If you guys have numbers, definitely let me know. 0.07 minus 0.051. That gives me 0.019. This is AQA. 8 times 10 to the minus 3 minus, sorry, this is going to be a plus this time, 0.051. This is going to be 0.059. And then we're going to substitute it into a Ka formula. Ka is equal to H plus A minus over HA. I'm going to rearrange for H plus, so Ka times by HA over A minus is equal to H plus. I'm going to put this right into my formula, into my calculator. So this is going to give me my Ka value is 1.84 times 10 to the minus 5 times by my HA moles. I'm just going to sit with moles, which is 0.059 divided by my A minus, which is 0.019, and then I'm going to minus log the answer. Minus log answer, and I get 4.24. Boom. Make sure you always do two decimal places. Always add to the acids when adding. Yes, Kitty. So just think about it in terms of this. So if you're adding HCl, you're adding H plus ions. So if you're adding H plus ions, your reaction, your equilibrium will shift to the left. Therefore, using that logic, if you add a base, your reaction will shift to the right. Okay. Cool. Very good. We'll finish off with a bit of pH stuff. I just want to quickly look at this part here. I'm going to finish off with this with two questions. Okay, this is really, I think a lot of people know this, but I think some people might have forgotten this. You can work out a Ka value using the pH curve. Okay, so when you do that, essentially you have two things. You have something called the equivalence value, and something you have called the half equivalence, or the half neutralization. Yeah, same thing. So equivalence is essentially where you have this. It's going to be where you have the vertical point. So this vertical region here, if I draw a line down, this is like probably somewhere like here. Let's call it like 19.5. Let's call it. Okay, cool. So this is 19.5 centimeters cubed. You will call this the equivalence value. So your half equivalence value will be whatever this is divided by 2. What's 19.5 divided by 2? 19.5 divided by 2. 9.75. So around at 9.75 centimeters square. 9.75 centimeters cubed is probably around here. If I read across this graph, which is, I don't know, 4.7. No, 4. Let's call it 4.80. Okay, obviously in your exam you're going to be more accurate. This is called it's the half equivalence value. So essentially, we find the steepness, we find the steep area of the graph. That's called the equivalence value. So that's where your reaction is. That's the end point of the reaction essentially. And then you take that volume and divide it by 2, and that's called the half equivalence value. And at the half equivalence value, essentially what you have is your pKa is the same as your pH. So here you see your pH is 4.80. So that means our pKa of the solution is also 4.80. Obviously in your exam you can probably read the graph better than me. It's a bit inaccurate here. So your pKa will be 4.80. Therefore your Ka value will be 10 to the minus 4.8, which will be let's see, 10 to the minus 4.8, which will be 1.58 times 10 to the minus 5. Okay. They might get you to use this pH, this Ka value. They might not, but essentially that's easy 3 marks. That's so easy 3 marks. I've seen an algebraic question like this before. Like they did this in terms of algebra, using x and x over 2. It was exactly the same thing. Okay, they just tried to make it a bit more complicated. All right. Cool. This is AQA, but to be fair, you could probably see an OCR as well. Do you not need to add the volume of the acid? Blitz, the reason why we didn't add the volume of the acid here is because the volumes cancel out anyways. You can, but you'll find out the volumes end up cancelling out. That's why I didn't add the volume of the acid. You can if you really want, but they cancel out. Okay. Cool. One last question. It's gonna be the last question of the day. It's gonna be this question. It's probably an easier question, to be fair. It was right at the start. Here we go. Oh, it's not this one. Oops, not that one. This one. When we have excess stuff. Now, especially in AQA, they don't really do this in OCR, but in AQA they give you a bit of a hint. If it's a Ka value, if it's a Kw value. If it's a Kw value, chances are your base is going to be in excess. Okay, I want you to try this question, see what you remember, and yeah, let me know how it goes. Alright. What I'll also do is I'm going to go through all through my PowerPoint. I did attach the link in the chat. I'll reattach it for the guys that are, what's it called, in the YouTube. Can I explain the HA? Yeah, I will, Nicole. Give me. Let's do it after this question. I'll re-explain that afterwards. Okay. It is all live. I mean, it is all recorded. So if you go into my YouTube, and you can always watch that back. I will reattach the link in the YouTube chat. Cool. Okay, so you guys can ask us the questions after that, especially the guys that are going to be rewatching this back. Just watch through it now. I mean, they can look through the PowerPoint. Any like sort of questions. Some of the questions have mark schemes, some don't. A lot of it we go through in the live anyways. It's just most of the stuff, like the stuff we skipped we didn't really skip anything. I'm gonna be real, we didn't. I thought we were going to, but we basically went over anything. I do a paper 2. I might do a paper 2. We'll see how it goes. Honestly, it's pushing 5 hour lesson in it, so we'll see, man. We'll see. When's paper 2? Paper 2 is next. It's on the 16th. I'm just looking at my calendar. My calendar, it's like right there. Inshallah, man. Let's see. Let's see how it goes. I want to see how paper 1 goes. Am I doing maths paper 2? I probably won't do a maths paper 2. I'll probably make a couple of videos on maths paper 2. I'm planning on making some walkthroughs in terms of. I'm gonna make some walkthroughs in terms of papers, so that might be a bit helpful. Just because, I was expecting, to be honest, I was expecting more views today in terms of live, and you know what, you guys are smashing it. You guys are gonna get the A stars. So I rate it, but yeah, it's alright. During the GCSE summer, were you confident about your results, or did you think you did worse than I did? I did worse. I thought I did worse than I did. Edexcel for maths. Alright, appreciate it, Niska, man. Love you too, man. Alright, let's do this. First thing you should do is write down the equation. Okay, sodium hydroxide plus HCl, balance it out, NaCl plus H2O. Okay, sometimes you might have a 2-to-1 ratio. Yeah, English was my hate. I hated that subject. I hate it with passion. Gonna do the same way as we've done the whole live session. N, C, and V. We're gonna put down all the information. So we have 0.15 moles per decimeter cubed for hydrochloric acid. 25 centimeters cubed. I'm just gonna convert that to decimeters cubed. We can also do the same thing for the rest of the information, and your work should look like this. What made me think I did worse than I actually did? Just English, bro. English. I was confident in my maths. I needed a piss in my paper 1 exam, bro, and I held it in. I didn't know you could go to the toilet. I was in my paper 1 exam. You know the question with the 3 circles. That was my paper, and I needed a piss in that exam. And I didn't go, and I held it in, so I was like, I thought I messed it up completely. so I was like, I need to pattern paper 2 and paper 3. So yeah, alhamdulillah, I did really good in my maths. So I can't remember what I got, but I did pretty good. My further maths went pretty good. My further maths actually did better. I did better than I thought. But yeah. What? They're interrogating my. Are you a policeman, bro? Are you fed? I'm joking, man. I got 8 9s, 2 8s, 1 level 2 distinction star in food tech, and 1/6 in Urdu. That's my language. I can speak it fluently actually, but I can't read it or write it, bro. Anyways, let me work out these numbers here. 0.2 times by 0.03625. If I multiply this out, this gives me 7.25 times 10 to the minus 3, and the other two 0.15 times by 0.025. This gives me 3.75 times 10 to the minus 3. Well, you can see obviously we have some excess stuff here, so what we're going to do is take this number, subtract this number, which is going to be a simple 1-to-1 ratio. So 7.25, I'm just going to do it like this, 7.25 minus 3.75 gives me 3.5 times 10 to the minus 3 excess. Okay, what you can do is think about what does NaOH go to. I like doing it in terms of this because it's helpful in terms of, you know, if you have barium hydroxide, if you have any terms of like what is it called? If you have more than one oxygen, not oxygen, hydroxide moles. In this case, it's just going to be a 1-to-1 ratio, so it doesn't really matter. So this is going to be 3.5 times 10 to the minus 3. Therefore, your moles for your hydroxide ion is also going to be 3.5 times 10 to the minus 3. We need to add all our molecules. We need to add all our volumes together, so we're able to get total volume. Our total volume will be 36.25 plus 25. I'm just going to convert that. That's going to be 0.06125 decimeters cubed. It's going to be moles. That's going to be your decimeters cubed. Our concentration for OH minus. Why do we work our concentration for OH minus? Because Kw is OH minus a concentration of OH minus times by H plus. Work out the concentration. 3.5 times by 10 to the minus 3 divided by 0.06125, and that gives you 0.whatever that mess is, 0.057. We know the Kw value is 1 times 10 to the 14 given to us in the question, so that means that Kw divided by OH minus is going to be H plus, and we can minus log that answer. 1 times 10 to the minus 14 divided by answer minus log, and 12.76 as your final answer. Boom. Okay. Firstly, make sure you are giving it in 2 decimal places. You will lose a mark if you're giving it to 1 decimal place. Okay, do not say 12.8, say 12.76. You need to say to 2 decimal places. Yeah, Ian, yeah, more or less. Yes, I did. I did them all for A levels though, to be honest. Alright guys, that is the end of today's chemistry lesson, man. Long lesson. Hope that helped you guys. Is KWH plus squared. It is not. That only applies when it's a sodium hydroxide on its own. Since you're reacting with HCl, it you can work out the OH minus separately. Where did the 6215 come from? I just added both of these volumes together. Okay, because it's total volume. Yes, JB man. Hopefully, it was alright. Was alright, JB man. The end bit buffers. Let me know if you need anything. By the way, I teach JB. He's not yet. He's a got student, bro. Alright, perfect. Yeah. Calm. Alright, I'll see you man later. It was a good session. Everything for the guys on TikTok. If you hop over to my YouTube, it will be posted on there. So yeah. Let me know how paper 2 goes. I mean paper 1 goes for chemistry. I'll see you man later. Bye bye. What? What Ian? What? You can revise physics if you want, man. No, do it. Don't give up. Don't give up on physics. Ian, what, bro? I'm trying to go, man. I'm hungry. No, I didn't. Not in advance. I mean, you can remember it. Oh, HA questions. Alright, let's go back to the HA questions. Essentially, what we have is initial moles and final moles. So we have, because it says we're adding a buffer an acid or a base to a buffer solution, what we have is our acid and our salt. We work out the initial moles of our acid and salt. We've already put them down, but we need to think about, well, if we're adding an acid, something's going to change. Some sort of concentration is going to change. So if we're adding acid, what happens is we're adding H plus ions to the solution. But in terms of equilibrium, what happens? Your equation shifts to the left. That means you get less A minus and you get more of your acid or your HA. So that's why we're going to take away from our A minus, and we're going to add from our H8. But how do we get 0.051? But we get 0.051 from working out, well, how much of acid have we actually added. 30 centimeters cubed of 1.7 moles per decimeter cubed, and that gives us 0.041 moles. And we add that together, and that's going to be our final moles for each. And what we do essentially is we just stick it into the Ka formula. We've got A minus moles, we've got Ha minus Ha moles as well. We can do it in terms of the total volume, but you'll find that the volume actually cancels out. So we just substitute everything in, rearrange, and you should get pH is equal to 4.21. Thank you. I appreciate it, man. Barakallah fi, man. Farah, is that the case? Yes, it is, Farah. It always applies. It only do this if the question says you are adding hydrochloric acid or sodium hydroxide to the base, to the buffer solution. Yes, Ian. Yes, I did, man. if you're interested, just drop me a message, Ian. Yeah. Alright, I'll see you guys.